log, the second generation is going past the new.
Yeah. Roger. Frank is coming.
Somehow I thought we were the smallest, but I guess not.
Maybe.
Couple it's almost strange.
Yeah, maybe.
Okay, so maybe we should start. We'll welcome Ann-Kathrin, who is going to tell us about on the quest on BSM with the mu3E experiment. Thank you.
Yeah, thank you. And thanks for the kind invitation to come here. It's a pleasure. All right, so we had already a bit of charge lepton flavor violation with muons, and we're basically just continuing the program here. So I am from the MEGII experiment. Most of you have seen this detector before on some slides, but I will give you a brief overview. Okay, this we had today a few times. So very quickly on the motivation. Lepton flavor is an accidental symmetry in a standard model, and we see it very often violated in BSM models. And we also know that even if we have lepton flavor violation in the neutrino sector, this does not mean that we have at observable rates in the charged lepton sector. So on the other hand, if we see it, this is an unambiguous sign for BSM physics, and that's why we're doing this. Yeah, some of these plots have appeared today as well, so I will be also very quick here. Why do we do this with muons? Well, we do this with muons because muons can be produced at very high intensities, and they have a rather clean final state. So there's only electrons, neutrinos, and maybe photons in there. That is very easy compared to high energy physics experiments. And that's also why we achieve already very good limits, 10 to the minus 12, 10 to the minus 13. With the near future experiments, 10 to the minus 15 to 10 to the minus 17 will be available. And yeah, you see this charge. No, I know it works.
Oh, okay.
Charge lepton flavor violation with muons is a sport that we do for many decades now, and we're still not done. So all the open marks here is currently running, so MEGII is running, or future experiments that will be taking data in the next years. So lots of new physics to discover there. And one channel to do this is, oh no, this was the wrong direction. Okay. One channel to do this is MEGII electrons. The current limit is quite old, 10 to the minus 12. It comes from 1988, and this is the year where I was born. So I am as old as this limit. And so, as you see, it's basically time to repeat this measurement and do it a bit better. We are performing a background-free search for MEGII electrons with the MEGII experiment. And we're aiming to find or exclude the decay with a sensitivity and branching ratio of a few 10 to the minus 15 in the first phase and 10 to the minus 16 in phase 2. And as always, the challenges are more or less the same. We have to suppress our background, otherwise we don't have a background-free search. And we have to operate at high muon rates. Otherwise, we do this for 100 years. No. So a quick look at signal and background. Signal you have over here. We take positive muons, they decay to 2e plus, 1e minus, same vertex, coincident in time. And if you do this with stopped muons, then basically the invariant mass of the 3-electron system is the muon rest mass, and the CMS momentum of the 3 electrons should come out as 0. And the other challenge that we will get here is that the momenta of each of the individual electrons are just some 10 MeV. This is very low. Backgrounds, we have a standard Morter process, me to 3 electrons, 2 neutrinos, the rare decay at a 10 to the -5 level. And it looks almost the same as the signal decay. The only difference is the 2 neutrinos, they carry away some energy. And therefore, we need a detector with excellent momentum resolution. There's also accidental combinations because we observe several muon decays at the same time. We can have, for instance, a normal MEGII decay. We take an E+ from there, and then maybe we have an E+ E- from a Barber scattering event, from photon conversion. There's lots of possibilities there. And there you have, in addition to kinematics, you have a handle on this background with timing, vertexing, and also with low material, because photon conversion, Barber scattering, etc., increases with the material. No. And that is why track reconstruction and low material is very important in our detector. So we have low energy plus E-, and they are affected by multiple Coulomb scattering. When they traverse the material, they get deflected within the material, they come out at an angle, they have lost some energy. This is all not good if you want to do precise tracking. So in general, if you have a low momentum particle, and this is your tracking detector, generic tracking detector, then the uncertainty after having passed the detector module is quite large. And so you get something that people call a broken line. There is, however, tricks that you can play here. Of course, you can have the scattering in your track reconstruction. People do broken line fits. You can reduce the material so that this green area is a bit smaller. But you can also play tricks on the geometry. And this is the relative momentum resolution that you get in a scattering dominated regime. So this angle here is basically dependent on how much material you have. But maybe you can play with this, the lever arm in here. And what we do is, well, this is another depiction of the lever arm. You have here your detector modules in here, and you have a distorted trajectory you measure with some uncertainty there. But if you have a very large lever arm of 180 degrees, the two circles meet again. So in this point here, you have the best momentum resolution you can achieve in this regime. And that is why we chose the geometry of our detector to be as it is. So a quick walkthrough through the experiment. Start with the muon beam. We stop it on a target. This is a hollow target, very thin material. So we have decays at rest. Then there's a magnetic field solenoid, 1 Tesla. So we have the curved trajectories. We can measure the momentum of these. And this we do with ultra-thin silicon pixel sensors. We have 2 layers close to the target to be able to reconstruct the vertex very well. 2 layers a little bit further out. So at least 3 points you need for a track reconstruction. We have 4 to reduce some ambiguities. We are missing still the timing. So we have some scintillating fiber detectors here for better timing. And then we want to play the trick of the large lever arm. And this is you make your detector longer. So we install recoil stations. We call these things here. It's again 2 layers of silicon. And in addition, scintillating tiles. This is the first place where we can actually afford material here, because afterwards here's beamline, so the particle will be stopped anyways. So the scintillating tiles is the first place where we can actually afford to have some material. And having tiles, you get a better timing resolution than with the fibers. So this is how it looks then in the cut-through version. Another aspect is we cool our detector with gaseous helium. We cannot afford any water cooling in the active target volume, and we opted for the smallest and safest Z material that we can have here. The whole thing is very small, 1.20 m, and the phase 1 detector 18 centimeters in diameter. So this is basically a tabletop experiment although it's not standing on the table. So let's go through the components. Muon Beam, we operate at PSI. PSI hosts the world's most intense continuous muon beam, ME+, from a very strong, intense proton beam smashed on a target. You get pions, you get muons, as in the other experiments. A subsurface ME+ beam, 28 MeV, and we get 10 to the 8 muons per second at the so-called compact muon beamline. That's here the muon beamline at which the Futrue experiment will be standing. And PSI has upgrade plans for the high intensity muon beams project, HIMP 2029. This is our cubed target. Looks a bit like a lollipop. It's a mylar target, very thin, some 70, 80 microns thick, 10 centimeters long, 90 millimeter radius. We combine this with an absorber upstream, and then we achieve a stopping rate in the experiment of 95% roughly. This is our magnet. It's already in place. We have used it already in integration runs and so on. We operate at 1 Tesla. In principle, we can operate the magnet at 0.5 to 2.7. Moving on to maybe the most interesting technology in the whole detector. It's our custom designed silicon pixel sensors. We call them MuPix. They are made in high voltage monolithic active pixel sensor technology. So that means you have basically P substrate, N wells in there. You apply a field, it's quite strong. You have fast charge collection. And what you can do in this technology is you can have some transistors inside your pixel, so you can have electronics there, and you have fully integrated digital readout on the sensor chip. So not like the hybrid sensors where you need an additional readout chip. This is all in one chip. It took us quite some generations. So the current one and the final one is MuPix 11. They are currently being produced. Most of them have arrived already. What we do is we thin them down to 50 microns. And this is a bit more than 1 per mil of radiation length, including the frag sprint in the support structure. So really, really thin. All right. Then we had 2 types of timing sensors, scintillating fibers in the central detector station. They're about 30 centimeters long, 3 layers of 250 micron fibers in one module. And we have a silicon, a CPM column array to read out the photons. And then for both timing detectors, we have developed a custom ASIC, the so-called MuTrig, for the readout of the signals. The MuTrig is also used here in the tiles. These are about 6 times 6 times 5 millimeter cubes or slanted cubes at the corners of the recurve station, wrapped in reflective foils. And each of them then gets here at this point its own CPM. And this is the timing detectors. A huge role also plays the data acquisition. We have nothing to trigger on. We have a continuous beam. The muons decay whenever they want to decay. And it's 3 tracks with some more or less random momentum. There's nothing to trigger on. So we have to do a triggerless and continuous readout of all the sub-detectors. So this is depicted here. All of the detectors have a custom designed front-end board, and they push the data then down to what we call the switching stage, where we mix the data such that in the next stage, each PC sees the whole detector information for a time slice. And then what we do there is we have GPUs, and on the GPUs we do track fitting and vertex finding. So the data comes in, goes first a triplet fit, then a 4-hit fit, and then we do vertex selection. And if we have something that looks like a Futrue candidate, then we push it out and send it to mass storage. And this way we can reduce our data by a factor of about 80. So it's very important to do it this way. The data acquisition is quite advanced. It's been tested in integration and cosmics runs. Currently, we're working here on the integration of the data from the timing detectors as well as okay, we speed up. Just very quick on phase 2, there will be him at PSI. So they will be replacing, they will be replacing the target for the production. They will have a better capturing solenoid, and they will provide 10 to the 10 muons per second. This is a bit too much for mu23E. We want to run at 2 times 10 to the 9 in phase 2. We are currently planning to have a longer detector, so better acceptance. But our biggest issue will be, as in the other experiments, accidental backgrounds. So one way is to have better vertexing, so you have a longer target where your vertex layers are closer to the target itself. And we need better timing, so we will replace the fibers here with ultra-fast silicon sensors. And we have to work, of course, also on the filter farm. Now I come to the sensitivity studies. This will be all phase 1, because the design of phase 2 is not yet fixed. But for phase 1, we have a full Gen 4-based detector simulation. We have all the track reconstruction and vertex fitting algorithms in place. We have some sort of analysis scripts there. So basically, this part is more or less done. You see here results from the tracking reconstruction. This is short tracks, and this is the recurling tracks. And if you compare at this point, we improve our momentum resolution by a factor of 10. So this trick with the long lever arm really pays off. And this is also what we need for the physics studies. We actually are requiring 3 recurling tracks to reconstruct the muon mass. And we get out at RMS of about 850, 900 MeV. And this is what it would look like if we do the experiments. So we have our backgrounds, the rare muon decay, the accidental combinations, and then here's signal at projected at different branching ratios, which comes out at the muon mass. Now, I always find it looks a bit scary, this accidental background, and it's very difficult to actually simulate this. If we plot this in 2D, so here's the reconstructed mass as before, and here's the CMS momentum of the 3 electrons, it looks already much better. What you see here is we have simulated 10 times more accidental background than what we would expect in phase 1, and actually 1,000 times more of the internal conversion decay. So we feel confident that we can do a background-free search in phase 1. And depending on the time that we get in data taking days, we will come out at somewhere 10 to the minus 14 to a few 10 to the minus 15 at 90% confidence level. Now, this was only phase-based decays. Let's have a look at what physics could be in there. So we have seen already a lot of EFTs in muon LFV. Of course, we have to do all the 3 golden channels because each channel has specific strengths and weaknesses. And the easiest way to compare them is in effective theories. As we are a PSI-based experiment, we like the plots of our PSI theory colleagues. You can have a look at their paper. So basically, they always put 2 different operators against each other. And then you have in red is mu3E-like, and blue is the conversion experiments, and the green ones is MEGII. And you can find your favorite combinations of operators where your favorite experiment comes out at top. So yeah, you all know there's lots of combinations that you can have there. So the idea basically is you can pin down the type of BSM interaction if you combine all the searches, in case you see at least in one channel something. So in the case of discovery, we have seen this in conversion. You can exchange the target, which is quite cumbersome, if I might say so. In MEGII, you have it already in the data. You have some hints on the type of physics in the data. So you can do standard plots, asymmetry ratios, and you can search for resonances in E plus E minus or E plus E plus. And this is how Dulles plots look like. So this is phase space decay, plain as you expected. Then we have here a dipole operator and here two different types of four fermion interactions. Now this is generator level. If we reconstruct and put our cuts, it looks a little bit different, but still there is a very big distinction between a photon operator and a four fermion operator. And if we have enough events, we can also distinguish between the two four fermions. And with the symmetry ratios, you can then pinpoint the chiralities of the operators, etc. So if we see something in MEGII, we might also get an idea what is behind this. Then there's a bit more we can do. We are very versatile because we have the 3 tracks. We measure E plus E minus with excellent resolution at high rates. We have a large data set with more or less polarized muon decays, broad geometric and kinematic coverage. So there's lots of things to do with this. We have the offline data set. Everything that passes the event selection is offline there, patiently waiting on tape to be analyzed. So this means all events that have 2 E plus, 1 E minus with a PT of at least 10 MeV. We have full raw detector information, so highest quality data where we can have the best momentum resolution that the experiment can offer. And this data set is basically agnostic to additional particles, if visible or invisible. Only the phase space available might put some constraints here. So we can do MEGII 2 neutrinos, standard model decays. We can have MEGII A to EE, maybe even with a little bit of displacement. We can have something like a dark photon in MEGII that decays to an E plus E minus pair. MEGII 5 electrons. It needs to be seen if the 2 additional electrons actually also need to have the 10 MeV or not, because it might be possible that we can reconstruct them in the vertex layers only, but this is something to figure out because this is also prone to have fake tracks. Then there is also online data. So we do track fits of every particle that passes the detector, and we can at least histogram these. We cannot store all the data, it's too much, but we can do histograms of the track fit results. The drawback is that it's reconstructed, you can never change it afterwards, right? You cannot reprocess it. But the MEGII X search will be performed this way. And honorable mention, we can also modify the detector. I would say then it's a different experiment because it conflicts the MEGII search, where we can change the B field, we can add photon conversion layers, extra pixel layers, change the beam to pions. There is a few possibilities. So yeah, muons with lifetime, MEGII A to EE. This is a MEGII electron final state. In principle, we can reconstruct this with our normal vertex fit. We've done a study on this. And it seems that if we have lifetimes of the A particle up to about a nanosecond, we still have efficiencies where we can reach good limits. And this is one of the studies we did here, where we have different masses for the axion-like particles, and then for different couplings of EE and UE there. So it's possible to cover some phase space here. Dark photons, you have also 3 electron data set, the 2 neutrinos. Well, what you do is you search for resonance in E plus E minus, and this is how a signal would look like at different masses. This is your background. You have the rare muon decay and the combinatorics, BABA decay. And none of them has a sharp peak as the dark photon signal, which gives you the possibility to perform the search. And we do get, yeah, well, we are not a dark photon experiment, but we do, we might be possible for us to also cover some white space here. And finally, what we call the Fermilon search, mu2EX, could be a fermilon, could be another particle. It's single electron events which do not pass online event selection, so you have to do histogramming online on the filter farm. This means you have only short tracks, not the best momentum resolution, but this is how a peak would look like of signal. This is the background. So again, nothing is peaking on the background, so you can do a bump search on this histogram. The difficulties might be in the Michel edge. You need to know very well your polarization, etc. So it might be that we need to exclude this area. Also, initially, we are planning to do calibration with this edge here. If we find another possibilities and we're thinking about mod scattering, then we might be able to get somewhere to the edge. This is a preliminary sensitivity study to this. So blue is twist results. They did it for several masses in Fermilon. And yeah, there is more than 2 orders of magnitude to achieve there for mu2 The red line is if we would actually use the Michel spectrum, but leave out a window around the expected mass, so that we don't calibrate away our Fermilon signature. And by this, coming to my end, yeah, you heard it already, mu2 we're aiming to search for mu2 electrons, 10 to the minus 15 in phase 1, 10 to the minus 16 in phase 2. We have a low mass tracking detector and online event reconstruction and filtering. And well, there's a lot of possibilities beyond mu2 electrons. And yeah, if anyone has other ideas to investigate, we are happy to hear this. Thank you.
Questions?
Could you say a few more words about the trigger? The
There's
reduction?
no trigger.
Oh, sorry, the reduction, the filter farm. What
Yes.
decisions are being made in the?
So what we do. What we do is we take. So we reconstruct. No. We reconstruct tracks in the central detector. So outgoing 4 hit tracks. This part of the track we reconstruct for all the tracks that we can find. And then when we have this, we do a very loose vertex selection. So we check if they somehow might end up in a vertex. What we do not do is we do not make selections on the mass. So in principle, that's why all these dark photon style searches are possible, because we do not cut on the mass.
So displaced vertices would be a problem. That's
Depends on the displacement. I do not know by heart how far these particles can be apart, but it is not a real vertex, but it's just we are just checking if they are compatible.
So you're mentioning possibility of modifying several aspects of the experiment. I'm wondering if there's any kind of strong limitation to squeezing the size of the first layers.
Yeah,
So in
it's the
principle,
beam.
like you could change the
It's the beam
target.
size.
Sorry?
It's the beam size. You cannot irradiate the first layers with the beam.
So the full size of this target is the beam size?
Almost.
I see. Okay, thanks.
There were initially for phase 2, there were ideas that we can maybe go to a smaller beam size, because they come in with 10 to the 10, we only need 20% of this, maybe we can cut more, but it seems from the current studies of him that actually the overall beam size is already bigger. So we are not quite confident that we can actually make it really smaller also in phase 2. Yeah, but you want to have smaller momentum, right? Or,
Right, I would be happy to pay a factor of 1,000 in rate to have a smaller beam and lower momentum acceptance.
yeah.
More questions?
Well, the other way actually is to change the B field,
Right.
which is also cheaper to do.
For me, just for me to understand, there is no initial counter of muons passing through. You don't know how many are sitting in your target or for how long.
Yeah, this we do not have like no scintillator counter or whatever. What we do is we take random triggers, so to say. So with the
So the information where the spin is pointing of the muons is lost, right? This way.
yes, well,
Because that could have been yet another handle if you would know where the spin is pointing, that you can start forming more correlations with
well, we sort of know that the spin of the muon will be slightly slanted with respect to the beam, because just from the position of the muons until they come into our experiment. So I think it was some 5 degrees with respect to the beamline. But then, yes, exactly. So we will have probably a similar polarization rates as MEG, but it's something that we will actually measure. So in the beginning, we will do also measurements of the Michel spectrum, etc., forward, backward, and then we should figure out.
maybe you can do some additional symmetry tests with you have 3 particles in the final state, and the kind of information, if you have also information about the spins, you could do something.
So
But
yeah,
with the neutrinos.
the rare decay, 3 electrons, 2 neutrinos. Yes, that might be something to look into as well.
Okay, so no questions. Let's thank the speaker again.
People hear me okay? Oh, that's gonna be real tricky. Okay.
Okay, well, I'm happy to announce Matheus, who is going to tell us about the new particle production at Muon facilities. Yeah, thank you.
Okay, thanks for the invitation. It's really great to be back to Minnesota. It's a great time every time. And also thanks, Ann, for introducing mu3e. Will make my job here a lot easier. So let me first start with kind of mandatory motivation slide. Why look for light particles at all? I can give you 3 examples. The first is if dark matter is a light particle, typically below 10 GeV, and it's thermally produced, we need new forces, weakly coupled new forces, and that's just something we should look for. UV theories, all sorts of them, may have global symmetries. Associated with these global symmetries, we may have Nambu-Goldstone bosons. These may have some symmetry breaking masses, giving rise to axon-like particles. We should also look for those. And finally, who knows what neutrino masses are? One hypothesis out of the many ambiguous ones is that this is coming from a seesaw-like mechanism. The masses of those heavy neutrinos purely unconstrained from the theory side. So we should look for those under the lamppost as well. Ultimately, though, we look for light particles because we can. That's just a low cost, high return scenario. And why muons? Well, in my opinion, it's just a great thing to do because it's a lamppost in the second generation. We have great intensities and great precision. And with all of that comes possibility to explore all of these different possibilities. And who knows, if we discover some new light particle coupled to the muon, that may shed some light into some big, very hard to solve puzzles in flavor physics. So in making progress, one can think about different axes. The first one would be intensity. We're seeing number of muons and just sheer proton beam power going up, and expect that to rise more and more in the future. So that's just a great thing to do. Precision through experiments like G-2, but also through experiments like mu3e, where the precision comes from the fact that you get a very low background, very precise measurements, high resolution detectors. And then there's the energy frontier. Maybe people are more excited about that after lunch's seminar from P5. So this is things like muon colliders, but also fixed target experiments like Na64 with muons, where you get to probe heavier particles with the muon beam. And then there's the lifetime frontier, where you can think about using muons as source of new light particles and look for their decays further away. And that's where spallation sources like the ones I'm listing here would really shine, producing a huge amount of muons, although in a dirty environment that you don't get access to in the vertex of the decay, but that you can look for in terms of new particles decaying further away at large neutrino detectors. So I'll talk about those two examples in this talk. I'll start with mu3e, or as with Maxime and Jure and Tony, we're hoping to rebrand as mu5e. So let me just give you a very broad kind of theorist's overview. So Ann already covered a lot of this, so I'll go fast. You could look for some peaks in the Michel spectrum and look for some fully invisible particle. I believe we'll hear some new ideas of how to make this search better at the low masses from Simon later on. You can look for a visible resonance. That's also, as Ann mentioned, in strong synergy with the mu3e program. It's the same final state, except here you would look for the resonance in a E plus E minus combination. So great sensitivity to that. And then you could look for things that are not charged lepton flavor violating, for example, emission of dark photons or some new muon coupled particle, which decays to E plus E minus. The final state now has missing energy, making this a lot more challenging. As far as I know, there is no search for this channel with a new resonance in muon decays, but through this great series of work here, you can see that there's possibility to probe new unexplored parameter space in dark photon models, for instance, which is very exciting. And then comes this talk and this paper with Maxime and Jure, where we looked into the next kind of logical possibility. You only get to play with electrons in muon decays in this case, and you have to go 2 by 2 in odd numbers of electrons to conserve charge. So the next logical possibility is mu to 5e. So if you want a kind of light particle search for this, you would emit some new particle X, which decays to 2 other visible resonances, each one of their own E plus E minus associated with them. So we think there is great reach for that. Of course, there's still a lot of studies needed, especially on the background side, but that would just be a great thing to look for. And also, it's the first kind of standard model study of this type of decay. So mu to 7 particles with 2 neutrinos and 5 electrons. So we computed that rate as well, which maybe we'll be able to probe. And finally, there's some other crazier models and modes to explore. You could imagine doing a 5-track search with missing energy. Again, you don't need charged lepton flavor violating for that. This is, of course, a lot more challenging than that channel we're discussing. And then there's also other visible resonances, whether it be 3 tracks or 5 tracks through a neutrino portal, where now the situation is very similar to this case and this case, but the kinds of couplings that you'll be probing come from a very different kind of physics. You'll be probing basically the mixing of this heavy neutral lepton with either the electron or the muon flavor. So that's kind of a less explored direction. So I'll leave this kind of summary here, and it's also on the website. I'm sure I've missed many references, but so please do complain. So let me jump straight into the first model for mu5e. We'll start just with a simple dark photon, which is Higgsed by some new dark Higgs mechanism. There's kinetic mixing between this dark photon and hypercharge, so that upon creating the dark Higgs, if the mass spectrum is just right, namely the dark photons are lighter than the dark Higgs, then you could create cascades upon producing this dark scalar. So it decays to two dark photons, which in turn decays to plus or minus. So it's a simple, kind of well-motivated model, and multiplication of leptons comes for free once you produce a dark scalar. This type of model, before discussing any charge lepton flavor violation, is already searched for several experiments. And there are searches at E plus or minus colliders that target the kinetic mixing, at the LHC, which targets the mixing of the dark Higgs with the Higgs. And most recently, also that mixing was targeted in kaon decay experiments. So this very impressive search by NA62 that Maxime and I were discussing was performed. And you can see here K to 5 tracks, just like the muon to 5 tracks. In this case, one of them is a pion. Reaches branching ratios as small as 10 to minus 9 and smaller, depending on where you are in the mass versus mass plane. So that's a very kind of impressive type of search where you come with this large lepton multiplicity for free. But now you could think about the same model in an effective field theory point of view, and the lowest dimensional operators, non-normalizable operators of this kind of construction already allow you to violate lepton flavor. So these are just examples of operators that violate E mu conservation. So you have left-handed muon or left-handed electron, and then upon symmetry breaking, you get these couplings Y, which are essentially a proxy for the new physics scale.
Does the standard molecule charge it under dark U1?
No, so this dark U1 is truly dark in a sense.
Why is that agent, right?
This is the dark Higgs, right?
Yeah, it charges under dark U1.
Yes, what did I do wrong here?
It's already Higged out, probably.
Oh, sorry, yes, this is a broken phase of the U1. Sorry,
So
sorry.
secretly it's a dimension.
Yeah,
six operator.
sorry,
Yeah,
exactly.
okay.
Yes,
You pay another tab.
yes.
All right, just
Yes, no,
okay.
thanks for
So you have
clarifying.
the lambda is not the scale. Right?
Yeah,
Lambda is-
yeah. So lambda is a proxy for a new scale. Thanks for clarifying. Yes. Yes, sorry for that oversight, but in essence, there is some proxy coupling Y, and you're probing that through muon decays. That's what allows you to produce a dark Higgs to begin with. So this kind of construction is just saying there's some light collection of particles, and they can be sensitive to the UV physics through these effective operators. Okay, so I won't go too much into the details of the mu3 experiment. We already heard a lot about that from Ann, but I did put a lot of effort into this GIF, so I'll just play that for you. So you can see the beautiful 3 tracks developing in the detector in this helical kind of trajectory, somewhere inside of being produced inside of the target.
So
This is-
supposed to go outside, detector still come back?
Oh, I sure hope so. Maybe Ann can clarify. She's
No,
not.
there's enough empty space. We don't hit the magnets, so it's.
Yeah. They're not very high momentum, as you can see here, right? So 30 MeV at most. So here's our own simulation of this. So why even develop a full simulation? Well, the main purpose is to understand the acceptance, geometrical acceptance to these events, which is crucial. You have lots of particles coming out of muon decay that will typically have small momentum each. So you need to know how many of them will actually cross the layers. So that's why we developed our own simulation. Muon decays are generated through MADGraph and some of the easier 2-body decays in the dark sector through a phase space package from scikit-hep. We neglect polarization. We place the muons inside of the Mylar target following the specifications in the TDR. So you can see here the density of the decays and where they happen. We draw the helical trajectories based on the 1 Tesla magnetic field, smear the momentum following the TDR, and then we can apply our signal selection following how many hits were observed.
So maybe I misunderstand something, but I thought that the muons decay on the surface of the mylar target.
I thought they were the inside, but maybe I'm wrong.
You stop the muon on the surface, I mean, inside the target material, not inside the hollow space in the target.
Yeah,
right?
there's
Project, you have to stop on the outside one.
Oh,
the material.
oh, that is a major yeah.
Averaging.
Okay, we're averaging. My bad, yes. Okay.
Why we have workshops.
So,
If anything, that might be a bit pessimistic because if they're more outside.
That's right. That's right. This actually makes the situation better. Thanks for clarifying that. Yes. Okay, so then we have all of these layers. Our simulation takes events inside of this region, but it's great actually to know that they will be on the surface. So you're more likely to hit the layers. So here, other gifts to show some. These are events that would be very well reconstructed. So if you put this on the edge, that would be even better. You have some other tracks with they're a little bit shorter. So if it's on the edge again, for example, this blue might hit the outer layer, so that would be even better. And finally, you could have situations where there's a lot of tracks overlapping each other. Yes.
Question. I mean, for usual dark photons, if you put very small value of epsilon and the mass is not that great, the lifetime becomes quite large. So is that included in that?
We do include the lifetime in the sense that we check that it's below any resolution within the target. So I forget the number exactly, but it's micrometers typically for the kinetic mixing that we're thinking about.
The signal here is not proportional to epsilon squared because we source it by some other operator.
Right.
And in your case, your signal is proportional to epsilon squared, and epsilon squared also regulates the lifetime. So in our case, it's too decoupled.
Yeah. So what you're actually probing in these experiments is this proxy coupling Y. Epsilon and the dark coupling kind of enter here into the lifetimes, but you get them for free as long as these particles are decaying promptly. Okay, so that leads me to this slide, which is on the standard model rate. So that's what MADGraph tells us. The muon to 7 particle branching ratio is. This is leading order in G Fermi and alpha. So that's actually quite a large rate if you think about the 10 to the 15 muons that you would expect. So you should have, in principle, lots of these decays happening inside of the target. However, if I place at the truth level, just a very kind of broad brush overview of what you would expect kind of the efficiency to be. If I place at the truth level a PT cut of 10 MeV, I see that this rate goes down to 10 to the minus 14. So that's a huge penalty in order to have an actual large PT electron or positron. So this is if all of the electrons and positrons obey this cut. So if you could measure this, given these limitations, this would probably be the smallest decay rate measurement for second and third generation fundamental particles, which is pretty impressive. And you get to leave like a great number on the PDG, which is quite unique. The other way to think about this is to look from the point of view of this as a background to the new physics channels. So if I forget about this truth level cut and then instead place truth level cuts on the missing energy of the system, you can see it goes down fairly fast to 10 to the minus 15 with a missing energy cut of 10 MeV at the truth level. So that tells you that most likely the standard model rate for 5 tracks is not going to be a showstopper for the new physics. I mean, in a sense, you would kind of wanted it to be the case because then you could see it at the standard model rate. But as this shows, it's probably not a problem. So now to the new physics hunt. What you would do is for a given hypothesis of the dark photon mass, in this case, just some random value here that you're doing a scan on, you'd look for combinations of E plus and E minus that reconstruct that invariant mass and find coincidences between pairs of those. And then for the 4-electron system, so 2e plus e minus is pairs. For a given hypothesis of a dark Higgs mass, you would do the same. And the hope is that you would be able to eventually reconstruct a point in this mass versus mass plane. So you can see the efficiency after we apply your signal selection cuts, which are very standard. You can see the full rate in solid with a 10 to the minus 12 total branching ratio, and the fraction of those that pass the signal selection cuts in color, in hashed regions, and they go down very fast. The efficiency goes down very fast as you go to lighter particles, purely due to thresholds. So also you can estimate roughly what is the kind of precision that you would obtain from on the mass of these particles. So if you had a branching ratio of 10 to the minus 12, which is currently allowed, this kind of resolution on the mass would be under a few percent, which is kind of amazing. So this is the kind of discovery that if you do make, you would actually discover 2 particles at once, which is great, right? So kind of high risk, high reward situation. So let me spend a little bit of time on this plot here, which I find very interesting. Now that I've just learned that the decays happen on the surface, I'm not sure how much this plot will change. We'll have to see. But at least with our current simulation, this is the total rate as a function of the number of reconstructed short tracks. So if I require all 5 tracks to be reconstructed as short tracks, then the standard model rate is all the way down here, below 10 to the minus 16 level. So that's very challenging to reach. The new physics rate, on the other hand, if I start with 10 to the minus 12, it's actually here at the order almost 10 to the minus 14, which is definitely doable. And you can see that drop off for a new physics is much gentler than the one for the standard model, purely because the standard model has to share energy with more particles. And you can also see if I require always to have at least 2 electrons in this sample, the difference in rate is not that much. And if I look into the standard model part, here's this dashed curve. It's 10 to the minus 14. So here you only have 4 tracks, but 2 of those are electrons. And maybe the backgrounds for those are much smaller because it's much harder to produce electrons inside of this experiment, although obviously not impossible. On the right, you have the missing energy region plots. You start with this large standard model rate that goes all the way back down here by requiring the 5 tracks. Okay, so backgrounds, we did think about this. We didn't have any simulation or very precise numbers, but using kind of well-informed numbers from the TDR and some kind of energy independent assumptions on the probability of producing BABA pairs, for instance, the most worrisome accidental background that we were able to find was a single internal conversion decay of a muon in coincidence with a Michel decay where the positron BABA produces another electron. So the rate for that with our kind of broad brush numbers, energy independent, was 3 out of 10 to the 12 muon decays. You would have this kind of a situation. So clearly more studies are needed, but it's actually a background-free search here doesn't look completely hopeless. And it would also be interesting to think about implications for a 4-track kind of channel where you require 2 electrons. So that's the reach in the parameter space of the model. So for those proxy couplings, Y. So you have on the Y-axis this coupling, which is, again, a translation to the new physics scale. And then the mass of the dark photon for various assumptions of the mass of the dark Higgs. And you can see for the heaviest dark Higgs, where the efficiency is largest, you get to reach couplings as small as 10 minus 13 or so. So there's also the competitive kind of the next best limit of a direct search for this type of model is actually a fully calorimetric search for muon decays, where you reconstruct the entire muon mass, kindly brought up by Doug Bryman here for us, showing that you can get branch ratios of order 10 to minus 16 back in the 70s. And now there might be some opportunities to improve that, and I'm sure we'll hear about it tomorrow. So very quickly in the rest of my talk, I'll mention some crazier ideas. So this is for mu to E and comets. So you could imagine mu to E conversion producing new dark particles. And the general idea here is when we talk about muon decays, you're typically thinking about that muon mass as a reservoir of energy to produce new states. But if I have mu to E conversion, this conversion is happening in the presence of a much larger reservoir of energy, which is the proton and the nucleus. So if I had some kind of exotic situation where a muon conversion can produce a new baryon, which is at the end of the road decaying to a baryon that is lighter than the proton, you could borrow energy from this system to dump inside of an E plus E minus pair, for instance. With this type of scenario, with these dark baryons that decay, you could imagine electrons and positrons produced inside of a mu to E experiment with energies above the threshold of mu to E conversion, so above the 104 or so MeV energy. The lighter this M1 particle is, the more energy you get to borrow. So if I go to as light as 880 MeV, for instance, I can dump more and more energy on that side of the distribution. And of course, the challenge with that is that protons should decay in this type of model. But if you choose your mass spectrum just right, proton decay would actually have to pay the price of having two particles off shell, which strongly suppresses that. And if you look at the lifetime of the proton as a function of this M1 particle, this M1 mass, you can see it goes from being very excluded, much below 1032 years, to being perfectly okay with the experiment at the largest M1 masses with a very strong scaling in the energy release of the system. So these are just some crazier ideas. Keep an eye out for more work on that with Maxime, Jure, and Patty here in the audience. So finally, I'll flash through the last part of the talk, which is, can I have just 3 more minutes? Okay, great. So I'll talk about spallation sources as source of new particles. And one particular example that we'll see progress in the near future is the Japanese neutron spallation source. And the reason why I bring this out is because it's close to a lot of neutrino detectors where you can look for long-lived particles. In particular, here the JSNS squared liquid scintillator, large volume detectors very close to the spallation source. And you also have, coincidentally, the ND280, the near detector of T2K, which is not designed to see the source, but it's actually fairly close to it. And it could observe particles produced here, as well as the Koto K-long detector a little bit further out. So if you look at these 3 detectors, they actually specialize in completely different things. So ND280 is actually really good at reconstructing low energy tracks in a magnetic field. So E plus E minus final states would be perfect for that. JSNS squared is really good at muon final states. And you could use kaon production of new particles to produce mu-E or mu-mu pairs. And finally, Koto is really good at double photon final states. So with this kind of complementarity, you could imagine constraining some new models. So here's just a very quick example of some new particle S that couples just like before through some higher dimensional operator, and there's a proxy coupling Y mu mu. The dominant production of these particles in the timing that I really care about for the muon production at the spallation source is muon decay to 4 particles. So here you see the Branchy ratio is a function of that mass. And its decay below the dimuon threshold is into 2 photons. So you'd like to look for 2 photons produced somewhere else away from the spallation source. So here's the kind of current limits and future reach of some experiments. I show here some LSND limits derived based on the neutrino electron scattering event sample. So you have to require the 2 photons to look like a neutrino electron scattering event. And that rules out a huge region of parameter space. Certainly a lot of the region for a G-2 explanation. And you could imagine also doing similar searches at Koto and CCM, which is an experiment at Los Alamos. And finally, you could do something similar for HNLs. So you can see that same LSND sample was used by Maxime and Yohei here to set limits on HNLs. Here's the mixing of the new particle with the muon flavor and the mass. So below the muon mass, actually the dominant limits in that region come from direct searches at spallation sources. And at ND280 and at JSNS squared, you could imagine doing something similar and improving on those limits, not because of more POTs or anything like that, but just because you could do a dedicated search for that inside of a low background environment, and ND280, for instance. That's the case for the electron, where you get the more modest improvement. And that brings me to my conclusions, which I'll leave you with and take any questions.
Questions?
So again, going back to that model with 5 tracks. So yeah, so let's just stop here. Yeah, so this Y is a composition of a off-diagonal Yukawa and a V electroweak over something.
Yeah.
Right. I just trying to understand what kind of actually suppose I'm imagining this is mediated by some particle. What's roughly the mass of the particle scale that I should be thinking about?
Oh, that will depend on the details of the U1 breaking.
Well, U1 breaking scale is roughly dark photon mass.
Right,
So
right.
Let's say.
Well, it depends on the values of the dark couple.
Yeah,
But yeah.
It cannot be very big. So,
Right.
So because otherwise dark photon will be heavy.
Mhm.
So, and
I mean, very, very roughly, right? You could imagine that these kind of very large scales that I'm talking about here. So this is the lambda after the U1 breaking, and that's like order 10 to the 15.
But that lambda we already agree is
Right.
positive scale. It's the V U1 breaking over lambda square.
Right,
New
exactly.
physics, right?
So then you, and I would have to tell you what the dark V over this lambda is. For Yeah, exactly.
Square root of that, so 10 to the 8
Yeah.
is U.
So then, would you naively?
Sorry, square root is this is 10 to the minus 12, right? And
the square root of this
Sorry,
number,
Jimmy.
10 to the 8 or so.
You could imagine several things happening, like you could have the muon could be charged under the dark U1.
That could be true.
Then it's really a dimension 5. So
Okay.
this is the scale.
okay,
If it comes from dimension 6, you know that this is gonna be
10 to the
probably
5,
10 to the 4.
Yeah.
Then you might expect mu to gamma or something else, no? Which comes in.
yeah, that's what. Then you may have other things too. You may have other things. Yeah, in that case, you may
But
have
you
other
charge
things.
the muon, because these couplings are small, no? This is incredibly small couplings that you need for this to dominate, no?
Mhm.
Like, all you need to do is you should decay to two dark photons and not to 2 electrons. All right, so these are small couplings.
Hmm.
Now, I mean, this loop is very okay. Maybe it's not the right value, so I should loop. Never mind. These are small couplings, so 10 to the minus 10 or no, 10 to the minus 9.
Okay, yeah, I'm just wondering, just what.
No,
kind
I
of
think
scale I
that's-
should be thinking about if
I think the point here, which I think is important, is if you pick a model, there is a lot of complementarity, right? So even at this level, there's a kinetic mixing here, which you could use to produce a dark photon directly. So there is also, for instance, complementarity between this and the dark photon search at mu3. Because at this level of coupling, you could imagine doing that.
Yeah, but for if you just look at your particular channel as a Maxim side, there seems to be dark photon kinetic mixing, at least is a free parameter.
Right.
As long as you don't get the long-lived dark photons, right? So then.
Yes.
Okay, so but I was just wondering where the scale is, so that you may actually have other signals, right?
Yeah, no,
Appreciate this.
but to Jure's point, whether it's a dimension 5 or 6 is also model dependent. So
Yes, yes.
yeah.
Okay.
So I was wondering in your dark baryon stuff, you looked at proton stability. Do you guys also, I mean, you have to, because I did this with Maxime, but you're looking also at beryllium-9 stability? I think maybe that.
We did not. And I will say actually spare my collaborators. This might be even the first time they are seeing the plots. So
Oh, cool.
the onus is all on me if you want. But no, but you could see, right, how by a judicious choice of M1, which has only a consequence for the endpoint of the electron and the positron at mu2e. The physics of proton decay and baryon stability is can be wildly different. You see, this is like from 840 MeV to 920 for a given choice of the other masses, right? But it's a very strong dependence because of the Q value.
Capital Q here is what?
It's basically the difference of the proton mass to dark
okay, the Q,
photon
yeah,
and
Q
chi.
value in this.
Yeah, yeah.
Okay, so I think we will move all further questions to the coffee break, which is now, and I guess we will convene at 3:30. Let's sing this.
Thanks.
There was actually.
Yes, it does. Yeah, and it's also very low. Companies say, like in all these models, like Beamline large, actually they get neutral.
Okay, I'm answering the Zoom question by Angelo.
I have to add something. Yeah. Some additional repulsive. You can, you may add. Shocking.
It was dense in the middle, but you might find I assume you know the codes. The rates are very high. So you see the version 1, I think the version 1.
They have a small amp.
Yeah, of course.
I just typed in V1
You just need to be smarter. What did you to remove V1? Oh, you didn't know it's V1.
I was doing it on my phone, so good point. Kind of very different.
V1 is 55 pages. Remove some of the cells the diagram. So I didn't have time to do that.
It's a good point. Good point. Good point. Depending what model you take. It's the dimension.
What's the
also indirect problems.
This is this Ben and Bart model with the variance like you share. I just thought, I was wondering whether you are thinking about something. Do like do MEV lighter.
Right, I think they're really back.
There is one nucleus that will cease to exist, and that's very.
But it has to be tuned really close to the neutron.
If you kind of, it's gonna be like somebody.
Yes, yes.
Separation and number of neutron. They had only 6 or 7 MEVs, right? Oh, no, this is very special because there is no mass 8 nuclei, right? The beryllium 8 is unstable, it's 12, right? You add the neutron. So there's no.
We all become lawyers.
Think was the neutron discovered.
Covering everything.
The binding energy is 1.8. You strike it without particles. Bingo, you have neutrons liberated, yes. That's how neutrons were
But it
discovered.
doesn't fall apart into 2 alpha, it falls apart into an alpha or.
Beryllium 9 is 2 alphas and a beryllium 8 falls apart right away. There is a gap famously at 8 equals 5 and at 8 equals 8. There are no stable. Just
unstable
energy. This is the consequence of alpha. So tightly bound, right? That is kind of really made us accident. Almost because energy excess over 12 is 90K. Yeah, it's very close to can imagine slightly different.
Right.
Yeah.
have to believe in anthropology.
Yeah.
You have to believe in
Exactly.
The real question,
Topics and then.
I mean, in particle physics, there's a huge range of subjects. Brilliant production, muons in collider, W, Z.
But it's not.
It's a huge, so there's something there, you know, then how to expand it.
Well, it's just.
Nuclear physics, atomic physics, chemistry.
Yeah.
Yeah.
There's a positive.
A lot of my collaborators do like that.
So that's all basically. This is.
We didn't do that. That was just giving me an idea.
Well, it could be a book where people are invited, experts are invited to.
Previous generation
to
of.
contribute chapters.
Almost.
It's
like a
3-volume. Yeah, well, I don't know if you could do it in 3 volumes.
Sounds a good idea.
I don't know if there'll be a market. For-
So now it's P5. Saying out the mirror. This is. Okay, it's good. It's 5.
Yeah.
Yeah, that sounds a good idea.
A huge project. To get all the right people.
I think it's the most important point is that you pick up the people.
Yeah.
The right. And then select the appropriate subject. And as I said, here is a very broad. Subject related to the house. So, I'm going to support you.
Maybe you could suggest people.
Me?
Yeah. You know a lot of people in Muon physics. I mean, I know people also like Aldo, Antononi. You know, there's photon radius.
Yes, yes.
Muon
Is he a scientist or experimentalist?
experimentalist. But obviously he knows a lot of theory.
Yeah, he mentioned a lot of theory.
I made an outline. And it's huge. There's a number of subjects and subjects. And I mean, there's very few people nowadays doing muon capture, like nuclear physics investigations. And there's some people at PSI, from Russians, who are still doing that, but there's no world expert that I know, like David Measday used to be on nuclear physics of muon capture.
I'm still looking at some kind of the article he made.
Yeah,
physics report.
whenever this subject comes up, that's the article that people cite.
That's a good idea.
It's like a retirement project.
Yes, yeah, but then I will be. I will have a second return soon. Yes, that's a good idea. I will think about it. If I can.
I'll send you the outline I made. And you can comment on, did I miss some subjects or fields, and maybe there's some extra.
Yeah, that's a good idea. Just exchange that, and also maybe bring some more people to join this core part.
There's some people have studied the impact of cosmic ray muons on evolution. Evolution. Animals and plants. You know,
I see.
interacting with DNA maybe have had an impact on the evolution of
I never heard of this, but
Uh,
it sounds like a very interesting subject.
and stuff like that.
I see.
And there are these people at Los Alamos who are gonna shoot muons at ships through muonic X-rays to find uranium,
I know.
to see uranium
Yes,
X-rays.
I have some friend, a Japanese guy who worked on Los Angeles at the time. He's sort of involved in this kind of a project, homeland security.
Yeah,
They
really
put some.
crazy. Having a muon accelerator shooting at
Oh, the same guy also working on this Muon accelerator, compact, is movable.
yes.
Sure that. Yeah, lots of questions. Okay, yeah, just send me a list and then maybe. I will say that.
So for the stop files. So that's what Ryan said what he wants to do. He takes your numbers, this somewhere. And then, so the idea is. I don't know where he took it from, but it looks like it took it from -4. So what we want to use is 10 to the 12 stop files.
Yes, that is
Which
the
comes-
number, yes.
Which comes
Same
from-
number as a meeting.
Yeah, exactly, but how we get to this, no? Is 10 to the 16 stop muons. And then from here, you read of the 1%. Yes. That's how we get it into the line of the little crops. Take this number for the number of stop muons. And then 1% is 10 and then 100 time is in 5 plus negative 10 to the 12. Does this make sense?
We have no idea how long we're doing.
I know, but it sounds reasonable that it works.
That's unreasonable, so that 1%.
1% of the time will be by operation.
Yes, sounds reasonable to me, but in phase 1, we have only 150 days.
Yeah.
Physical running time.
Yeah.
So that means maybe 1 or 2 days.
Yeah.
Sounds
Sorry. That's all, I know, it's completely.
No, in fact, that I have no idea, how frequent we have to make a calibration data. So I think that maybe more than 1%. So that we get us the money, stability.
We use this slide, she wants to special domain of your one. That she's removed.
Seriously.
Thank you.
Right, awesome. Yeah. Yeah, somehow it's, you have this email lead, so sometimes.
You could get more. Okay, but that's fine. This is
Hey, Angela, can you hear us?
Thank you. Okay, no problem.
Leaving on Friday, again, have like this.
Can you hear me?
Oh,
I can hear you. Well, can you hear me?
sorry, Angela, can you try speaking again?
Yeah, yes. Good morning, good afternoon, everyone. I can hear you very well.
Good, yeah.
Right.
Just,
We haven't started the session yet, but in 5 minutes.
yeah.
Okay, fine.
Could you go ahead and share your screen?
Sure, I can. I hope you can see it.
Yes, we can.
Yeah, we can see it.
Okay, very good. You can tell me when I can start.
Yeah, sure. So for keeping time, I think what we will try to do is I will try to just write a little note on the side when there's like 5 minutes or 10 minutes left. Can you see that when I write that?
Well, probably not, but nonetheless, I have my timer in front of me. So
But do you see the 5 minutes that I wrote on the screen?
no, I can now. Yes. Sorry, there was a bit of delay. Yes, now I can see it. Yeah.
Okay. Yeah, so I'll just try to give that heads up. But okay, yeah, we can just let you know when we're ready to start then.
Angela coming from.
Angela, where are you right now? At the Pisa or?
Yes, we're doing a beam time, 2 simultaneous beam time.
Oh, okay. Wait, what time is it there?
10 and 30 p.m.
Oh, wow. Okay.
10 o'clock.
Yeah.
Ting, you think you will share? Then you need to produce the sound. No, they produce the sound.
Oh, yeah.
Yeah, we're doing here. I think that's the even. Well, let's start looking. So you want to have it. Oh, brilliant. Okay, yeah.
So you and I are in the same boat. We maybe can.
Say that quickly. I want to say that.
Me too.
They didn't really do one. In the end, they some kind of employee. So the target probably is better than worse than what they say it is.
I mean, if you want to introduce,
So.
Hello?
Hello.
Hi.
Okay. And now let's start the last session for today. Angela will tell us about current and future prospects at PSI. Angela, please start.
Thank you very much. Thanks for the introduction, and thanks a lot to the organizer for having us the possibility to give this short report. We would like actually to apologize for not being able to be there. There was really during this date quite some activities at PSI due to the changeover from MEGII to Futrue, and also, let's say, one of major beam time that we have for the muEDM. So then I hope that this is a valid justification for, let's say, staying here and not being able to be there. But nonetheless, okay, let's move on, let's say, with the talk. So then the idea would be to actually go quite through some topics. So then giving you a recent update about, let's say, the MEGII experiment, and also discuss with you about the prospect of the muEDM experiment, and then together with that to share this future Beamline development, and hopefully this could trigger some new ideas. I was very happy to follow the previous talk, and then probably this could be an opportunity also for us to somehow host some new project at PSI. So then, let's say the first topics about, let's say, then MEGII, and then although, let's say, also this morning have been this topic already discussed, let me just to remind that in this specific topic, so then we are going to tell us again about the importance of low energy precision physics at intensity frontier as a very strong and sensitive tool to search for new physics, and the specific topic and talk focusing about the muon charge lepton flavor violation, and also matter and matter asymmetry, which are basically, let's say, rate forbidden decay search in the first case and symmetry test in the second one. Now, let's say, concerning the motivation to search for charge lepton flavor violation, as have been already mentioned several times today, so we already know that neutrino oscillates, and this represents an evidence of physics behind standard model. This is an example of neutral lepton flavor violation that doesn't have yet the counterpart in the charged sector. And what is actually interesting is that if now we are going to take into account, let's say, the massive neutrinos, actually processes like mu-gamma, mu conversion could happen, but they are strongly suppressed. So then with the current sensitivity, if we are going to see something, this would be a clear evidence of new physics. And actually, let's say, in a different way, we can also say that although in our cases, we don't have the pleasure to have this new particle in a final state as it could be at energy frontiers, due to the fact that this new particles enters in our Lagrangian as a virtual behind standard model particles, this actually gives us the possibility and the unique feature of being able to probe energy scale that will be otherwise unreachable. And in fact, this is what is happening when we are going to do the exercise, for example, of see how, for example, the upper limit on a branching ratio like mu-gamma, mu-conversion translate in the energy scale of this new physics associated to the process is actually going to be exploited. And now I will not enter anymore, let's say, in the details about the future sensitivity, but just, okay, this is basically where we are. And now I guess that we have to start also to update this plot due to the fact that we had these new results for MEGII. Okay, but let's now see, in case, let's say, we are thinking about this experiment and want to do charge lepton flavor violation with muons, then the first items to look for muon beams, and this is probably actually what we are going to end up if we are searching for, let's say, the available muon beam in the world. And let's say what actually it's quite special for PSI, in particular for the MEGII search, is that PSI is actually delivering the most intense continuous low energy muon beam in the world, up to this few times 10 to 8 muons per second, with the characteristics of a momentum of 28 MeV over RC. And the main point due to, let's say, this large number of muons is actually connected with the Earth, of these high-intensity proton accelerator facilities, which is the ring cyclotron with a power of 1.4 megawatt. And he's just a reminder that although we are saying that this VMITS continuous actually has, let's say, time structure of this roughly 50 megahertz. And this is just a view of how the experimental area looks like. And actually, this is the Pi 5 area where both MEGII and Futrue are hosted at PSI. So then the first element in order to perform this kind of experiment is to have as much as possible muons. And what we are doing is actually to collect from the target where the muons are produced after the proton impinged on a carbon target. So to select and transport these muons up to the center of our apparatus that here is represented by this special magnet that we call Cobra. And the good news is actually after every tuning year by year, this year we actually improved even further the number of muons with this record of these 2 times 32 times 28 muons per second when we normalized the 2.2 milliampere here at the collimator before, let's say, entering specifically in the apparatus of MEG. Now, how the experiment looks like is actually sketched here. So then we are stopping the muons in a very thin target, and the aim is actually to measure very precisely the particle coming from the decay of the muons in a positrons and a gamma. So we have to measure very precisely the energy of the two particles, the relative time, the relative direction, and this would actually translate in helping us of fighting against the backgrounds. And here we can see the main backgrounds, so the radiative Michel decay when the two neutrinos are taking away just a small amount of energy, and the accidental background when we have a positrons coming from a standard Michel decay and the gamma from annihilation on flight or restrival. So then let's say the muons are then stopped in a very thin target, and then all the kinematical variables associated to the gamma are measured with a liquid xenon calorimeter, while all the kinematical variables of the positrons are measured by the spectrometer. And the spectrometer is actually made by a special magnet which produced a gradient field. This was a first application in particle physics, and then this magnetic field actually helps to bend the charged particles going through this long and very light drift chamber from which we can extract the track, and then let's say the momentum, and then the direction of the particles. But what we're still missing is the time, and the time is coming from actually some plastic scintillators coupled to silicon photomultiplier. Then together with that, we have also some other auxiliary detectors like this radiative decay counter that help us to reject the background, and then a complement to all the rest is given by this new electronics, this wave DAC, which give us a possibility to digitize the waveform up to 5 gigasample per second. And everything it's actually supported by several calibration methods at different energy, different conditions that actually allow us to be sure that the performances of each sub-detector is achieved and maintained over the time. So then this is actually the prospect when we compared ourselves to MEG1. So this was, let's say, MEG1, and this is actually where we expect to be. Then we started in 2021, and the final aim of MEG2 is to achieve a sensitivity of something like 6 times 10 to minus 14. So where we are, so then we started 2021 actually with our first relatively short but very successful physics run. And then it continued in the 2022, and then with the second physics run. And in 2023, actually, we started again in June, and we just finished last week. And then I can already anticipate you that with the run coming from last year, the 2022, we already expect to surpass the MEG2 sensitivity. But what about then the 2023? Because we just finished this. Okay, actually, this is a bit of, let's say, the story of all the physics run. So then we started in June, and this was actually the first week of data taking compared with the run 22nd. At the time, let's say the calibration of the data from run 22nd were ongoing, and also the analysis of the 2021st was ongoing. And this is just an idea of how actually our beam looks like at the center of the main magnet where the muons are stopped, and then let's say the positrons, and eventually the mu gamma process is produced. So this was at the middle of the run, so then roughly end of August, and you can also appreciate the difference in terms of the derivative of the accumulated, let's say, muons with respect to the previous year, and this is how actually ended up, let's say, then last week. So then the data taking has been completed for this year, and also, let's say, then the analysis, we moved from the calibration of the 2022 run to the analysis. And the other good news was actually we managed to finish the analysis of the run 2021. So then let's go a bit more into the details about this point, because actually we look at the data and then we released our result already on archive. And here you can see the 5 kinematical variables that we used for searching for the mu gamma decay, together with a combination of this so-called error signal. And this is just a log of the ratio of the signal likelihood with respect to the two background, accidental background, radiative initial decay background, with the weight that is coming from the side band. And actually, if now we're going to look at let's say the variables, for example, projecting the E gamma with respect versus the energy of the positrons, or the relative time with respect to the relative angles, we could identify somehow the so-called, let's say, hot zone. And as you see, let's say, I thought we could provide a sort of ranking of the most likely mu gamma events, let's say this one here, this one here. You can see that actually we never had, let's say, sort of very good events here and here. And then, as you can imagine, this actually translates in, let's say, an upper limit on our search is based on the data sample of the run 2021. And then here actually it's the distribution of the 90% confidence level upper limit that we calculated for an ensemble of pseudo experiments with a null signal hypothesis. And here you can see in the red dashed line, let's say, the sensitivity, and here the upper limit is calculated. And now if we're going to combine, let's say, this result with the previous MEG1, actually we could obtain a better upper limit, the most stringent one, actually the most stringent limit up to date, let's say, which is this 3.1 times 10 to minus 13 at 90% of confidence level. And then we are keeping on going, let's say, also with analysis and with data taking, and then we are stick on our final goal by the 2026 on, let's say, aiming at reaching the sensitivity, as mentioned already, of something like 6 times minus 14. So this is actually all concerning MEG. I want to share you, and then let's move on also about other things that we can do with all the muons that we have at PSI. And now let's say another point that we actually can attack is this matter and matter asymmetries. And we already know that this baryogenesis requires additional CP violation contribution behind the standard model, and this actually could translate in electric dipole moments of fundamental particles. And actually also in this case we have a lot of effort ongoing. This is let's say a plot to summarize the upper limit that has been set looking at different EDMs. And what actually it's interesting here, that the effort on the muons is limited at these, let's say, points here. This is the most recent direct measurement here, let's say, that translate in this upper limit. And actually we thought that it was time to think, let's say, about an experimental effort that could be actually competitive with other effort, like, for example, the G-2 experiment at FNAL and JPART that are aiming actually to obtaining this kind of sensitivity for the electric dipole moment of the muon. But in this specific case, let's say the proposal that I'm going to discuss right now, let's say the aim is to really focus on a direct search, which I'll look at the stage of the precursor would turn out to be very similar to the sensitivity that other experiments are going to achieve. the advantage would be that if we could prove that this new technique is valid, this would allow us to, in a relative short time, to push down by 2 orders of magnitude these searches. And now, which is the idea? So then we also know, let's say, about how, let's say, a charged particle with spin behaves in presence of electric and magnetic field. This is the precession, which is a quite complicated formula when we want to extract all the information. So also here, the exercise tried to simplify it. And now if we just focus on EDM, so what we want is to allow that only these terms where the eta is, which is connected to EDM, is going to survive. And then let's say then you want to have a combination of electric and magnetic field, such as actually this kind of term is going to disappear. And then when you are in this condition, what actually happens is that if you are able to accumulate muons in a sort of right orbit, so then if you don't have, let's say, EDM, so then what is going to happen is that the spin follows the momentum vector, while as soon as you have an EDM, so then it will result in a precession of the spin, and this is going to happen along, let's say, on this plane, the green one, and this plane is actually perpendicular to the to the direction of the electric field, and then the nice thing here is that this sensitivity of the muon-EDM, let's say, translate in an asymmetry of the up-down of the positrons coming from the muon decay. And now let's say then, if then we're trying then to put everything together, comparing what, let's say, it's been up to now the effort in the G-2 configuration, let's say then you see that in the case of the frozen spin technique, actually, let's say then at least from the point of view of visualizing everything, then the experiment strongly, let's say, simplified. This, let's say, there are a lot of issues, let's say, but at least, let's say, from the conceptual point of view, then it turned out to be very simple, because then we have just to look at this asymmetry, let's say, up down between, let's say, with respect to the plane where the muon has been accumulated. And now informally, we're going to do then this exercise, take into account how really the positrons are emitted. Then what is going to happen is that we are going actually to be sensitive to this, to the slope of the oscillations that we are going to have, let's say, from the MEGII coming from the muon decay. And now how we want then to really do this experiment. So then the idea is that we are going to inject muon in a uniform magnetic field. But if we don't do anything, so the muons are entering and then going through this magnetic field, so we want to stop in a sort of magic zone. And then in order to do so, let's say we are going to have a weekly focusing field. A weekly focusing field, and this is, let's say, this is associated to a kicker, to when, let's say, the muons is entering into the region. And now, together with that, we need also to have this electric field that allow us to have this condition of the frozen spin. And then, let's say, basically, in terms of the preparation of the muons, so then the job is done. Then we have to think then later on how to then detect the positrons coming from the muon that are going to decay. So then now looking more about the detectors. So then the idea is that we need an entrance detector that allow us to know when a muons is entering, because then we have to produce the kicker to this weekly magnetic field. And then let's say when the muon is continuing, so it's going to reach the zone where actually it's basically accumulated in this kind of special orbit. And then we have just to wait, the muons is going to decay. And in order to do so, we will have basically a tracker that allow us to measure the direction, and then let's say the point from which the positron has been emitted. And then we will think of doing this kind of detector as a combination very similar to a Futrue combination of plastic scintillators and so silicon devices. So actually this is the schedule, the tentative schedule that we have. So we are in a so-called phase 1 with the precursor that has as a final aim the one of proving that we are able to do this frozen spin technique, and eventually also putting out some very preliminary results from a very short, let's say, data taking. And this would be crucial, that is going to happen before the long shutdown that PSI will have in 2027 and the first part of 2028. And then during the period of the shutdown, this will allow us to prepare the detector in its final version for the so-called phase 2. Here, just some number associated to the number of muons that we can expect, depending on where we are at PSI in the different area, and then combining with a certain number of days of data taking, the final sensitivity that we mentioned, with in principle two magnets which are available. One, let's say, from PSI that is abundantly used also for other research, like MEGII, that I'm going to mention very quickly later, and also, let's say, an offer, let's say, from Argan to use, let's say, the solenoid that they have for this so-called phase 2, and then let's see, let's say, where we are. Okay, so then this actually brings me to the last part of the talk, where we would quickly just to mention the future beamline development, this high-intensity muon beam project, and MEGII. So now, let's say, in terms of the high-intensity muon beam, let's say, what I want to remind you is that at PSI, for this kind of application, we are actually going to select the muons that are coming from the decay of the pions at the surface of the target. And the characteristics of these muons are that these are actually polarized, and then can be used not only for, let's say, particle physics, but also for material science. And now, if we want actually to increase the muon production, we have actually to try to find a solution that it could be somehow pursued in a relative short time, and could be also cheaper. So now, looking, let's say, at what we have in our experimental area, we can think of actually increasing the beam intensity, either increasing the power of the machine, so at the source, or, for example, looking at the different target, or optimizing the beamline, or finally at the beam time. But if we are in a condition, as it was in our case, that we have constraints at the source, we cannot increase, let's say, the power of an accelerator, and we have also to keep the fraction of the beam that allows people doing neutron physics to continue their research. So then, let's say, our efforts was actually restricted to these two options, let's say, try to improve the target and try to improve the beamline. And then actually what we look at was to try to find some alternative at the target in terms of material different geometry. We're looking at the amount of muons that we are going to produce, actually putting together the pion yield and the relative muon yield. We concluded that the configuration that we actually have, it's a carbon target, it's still the best one. We could improve a bit, let's say, changing to something like boron carbide, or a combination of carbon with beryllium that would produce these 10–15%, but we remain and stick on a configuration of the carbon target, because actually what we found to be more generous in terms of improvement was actually a different geometry, where this lantern target was actually implemented and used, and proved actually to improve by this roughly 50%, that for us translated to have an equivalent of accelerator with the power of, let's say, 2 megawatt instead of 1.4 megawatt. So an important, let's say, step forward. So the second point was to try to look at some improvement along the beam line, either increasing the capture, as this is the case, let's say, with the gradient field, with the two solenoid looking nearby, let's say, the target, and also improving the transmission. This is an example of a hybrid beam line as we have currently at PSI, and how it will look like when we are going to move move to this high intensity muon beam with a poor solenoid beamline that allow us actually to compensate, let's say, for quite an improvement of the transmission, and then ending up to this 10 to 10 muons per second with respect to the 10 to 8 that we have right now. Where we are, okay, then the project is actually very well advanced. Here you can see how the two lines would look like, let's say, in CAD, and then some finalized version of our, let's say, transmission and Monte Carlo simulation, particularly here the line dedicated to the particle physics world. And then finally, actually, we could also think about, let's say, sort of tertiary beamline. What I mentioned up to now are the muons that are coming, let's say, from the interaction of proton on the carbon target, but then we can also manipulate these muons for having a sort of a low energy, high brightness muon beam. And actually the idea in the project we are also pushing on is, let's say, the possibility to have an improved phase space. This phase space is reduced based on a dissipative energy loss in matter, helium gas, and the position-dependent drift of the muons with the right combination of electric and magnetic field that would allow us actually to improve the brightness by 10 orders of magnitude, but not for free. Let's say then paying, let's say, something like a reduction of 10 to -4 in terms of intensity. So then the idea by itself is also very simple, because then if we are actually thinking how, let's say, a charged particles behaves when it is in the presence of electric and magnetic field, so we can repeat the exercise when we have also some gas, and then we can then immediately realize that actually the collision, the frequency of a collision is different depending if you are more along the E or the E plus B direction. And this is actually what we are going to use in our setup, because we are considering how actually the different way, let's say, the particles are moving when there are more nearby the warm region with respect to the coldest one, together with the combination of the electromagnetic field that allow us to exploit this behavior here. Actually, we could prove both the compression and the longitudinal and transverse direction. And now the main effort is now to conclude with some Monte Carlo simulation that allow us to extract the particles in vacuum. And then let's say this year we didn't have time for this project, because then the main effort will be for next year, where we are aiming actually to do this extraction in vacuum. And basically, yes, this is all. So then you see that we are trying, let's say, to keep and to preserve the excitement in terms of a particle physics program at PSI associated with muons. And we really hope that with this new beam development, with the HIMP and MEGII, there will be some new ideas, and then there will be some new project that we can welcome and we can ask PSI. Thank you very much for your attention.
Questions?
Perhaps a comment. We invite you to also look at yesterday's slides by Ting, where we set the indirect bounds on the MuonEDM using the atomic EDMs. So I'm pleased to see that the target that you have for run 1 is just better than the current bounds, which are 9 times 10 to the minus 21 indirect bounds. But in the meantime, electron EDM limits may also improve, in which case the indirect bound, I stress that, indirect bound on MuonEDM will also get better. So
yes.
So in some sense, you have competition.
Absolutely, yes, absolutely. Yeah, thank you for the comment. Yeah.
Hi, Angela. This is Yoshikuno. In the MEGII analysis, you have mu counter, it's a radiative detector counter.
Yes.
Was it useful? How do you use this?
Yes, thank you very much for the question. Yes, we use it, and actually it allows us to reduce, or if you want, in the final configuration, to improve the sensitivity roughly by 20%. So then this is why, for example, we are pushing for trying to have a sort of a radiative decay counter also upstream. Upstream, it is much more challenging because then muons will go to the detector itself. But in particular, our colleague in Japan are trying to find a solution that could be valid enough without disturbing too much the muons that will go through the detector first and then are going to detect the positrons from the muons after that have been stopped into the target.
Okay, thank you.
Thank you for the question.
Okay, let's thank Angela for the
Thank you.
Right, so you detail this one. Yes.
Okay. And this thing goes like this.
Okay, our next speaker is Sam. He will tell us about net neophysics at Mu23E and MEGII. Sam, please go ahead.
Good. Okay. So Bertrand earlier told us that theoretical physics is trivial or is easy compared to experimental physics. And I thought start by reinforcing that by showing you this very sophisticated formula I have over here. So why do we care about muons? Again, there are many reasons, as we discussed already this week. My answer to this for today is the following, right? So if I have some dark sector stuff which happens to be lighter than the muon, and I want to know roughly what the branching ratio is of the muon into these things, it's proportional to some tiny coupling, right? As we've seen already earlier. But importantly, it scales with this absolutely massive number, which is why it's always very useful to look at exotic branching ratios of particles that are really narrow, right? On top of that, we can make a ton of these things as well, as we've seen from our experimental colleagues. So the same principle, of course, works for pions, kaons, and Bs, and to a lesser extent also for the Higgs. Can I advance slides or? Okay, it's reverse from what I thought. Okay, good. So those are the two signatures that we'll talk about. So this is essentially following up on work by Ann-Kathrin. So we've already heard some ideas. And so what we're trying to do is suggest a few ways to improve on this by leveraging a couple extra features. So let's start with the flavor violating case. Okay. So this is a plot I took from Ann-Kathrin. So this is the Michel endpoint, as you saw earlier. In Mu3E, and so this edge over here is smearing from the detector, right? And so if you're looking for an invisible state, and this thing has a mass that's like larger than a few eV or so, it's going to sit as a monochromatic line, someone on this Michel spectrum, and it will be really nice. If you look at very low masses, you'll start sitting near this endpoint over here. And so this, as Ann-Kathrin said, is something that you'd like to use to calibrate your detector. And so either you have to find an alternative way of calibrating the detector, or you can try to calibrate on the Michel spectrum and then use your simulation to extrapolate over here. And so this is potentially subject to systematics that will be only understood once the experiment is commissioned and tested. And so for that reason, we were interested in trying to devise like some alternative approaches to doing a search for very light hidden sector particle of this type, should the systematics become problematic in this region of parameter space. And so the idea is to trade systematics for statistics by looking for subleading decay. So you're in this case of MEG2, you're attaching an extra photon, and here you're attaching an extra plus or minus pairs from U3E. And so this brings you to a different kinematic regime at the penalty of both signal and acceptance and background rate, but it pushes you away from this Michel endpoint, which you are potentially dominated by systematics. So let me first talk about MEG. So MEG, as we just heard, is optimized very much for muTE gamma, so which it does like a superb job. But it means that the detector geometry is very strongly focused at looking for back-to-back electrons and photons. So you see that in this colorimeter design, and also the tracker is focused just mostly at back-to-back positrons.
Are they also sensitive to E gamma gamma?
E gamma gamma. A priori, yes, but I'll show you in a second why the acceptance for that might also be rather low. So specifically, what's happening is the B field here is non-uniform, and it's designed to sweep away positrons, which are substantially less than half the muon mass. So any extra particle you're attaching to will come at a huge cost in acceptance. Specifically, if you're trying to radiate a photon off the electron, it's going to like to be collinear in the standard model, which is the opposite of what this detector would like to see. And so this is of course complicated to model for us, so we have to make some assumptions, as I'll try to clarify in terms of what this detector could do for this type of signal. So specifically, a very, very, very oversimplified picture of the trigger at MEG2. So this was extracted from the radiative muon decay measurement from MEG1, and we sort of extrapolate to MEG2. This is the effect I just mentioned, that the B field is non-uniform. So there is essentially the turn-on curve for the positron energy is kind of hardwired in. I mean, it depends on basically the angle that you're emitted at, and then the non-uniform B field. You can't really do very much about it. The turn-on curve for the trigger efficiency for the photon, on the other hand, is like a software trigger. And so this is put in to ensure that the total rate that's read out of mu3E is not exceeding what their data storage can accommodate, because these events are very, very large, because they want a very, very good calibration of the colorimeter. So what you could consider doing is you could consider, in principle, lowering this threshold, but at the cost of reducing the beam intensity, because you can't maintain a low threshold here. This one, there's not much you can do with. So then the question is, how much do I have to lower this threshold, and how does the signal efficiency scale with a lower threshold, and is it actually worth doing, or is this not something that is experimentally viable? And so this is what I'm trying to show here. So these plots are a little complicated, so let me try to walk you through it. So we're reconstructing missing mass with the electron and the photon, and this is what happens if you do it parasitically on a MEG2 run. So the green here is the signal, so it peaks at 0, as you'd expect. And so the red curve over here is the accidental background from random coincidences that we heard about earlier. And you see, because of the very stringent selections in muTE, so this background is supposed to be flat, but it actually gets shaped by the cuts into a peak, which sits right on top of the peak that you want to sit. So that's not really ideal. And so the blue is the radiative muon decay background, which is subdominant to this. Now, if you lower your beam intensity by, let's say, a factor of 50, and you relax correspondingly your photon, you cut on the photon energy such that you maintain roughly the same readout rate, the picture changes. So here you should see that the axes are slightly different. Apologies for that. But so there's way more events here than there are here, because basically I loosened this photon cut. So like both signal and background, everything went up. But correspondingly, the random coincidence went up less, because this scales quadratically with the rate. And so that, relatively speaking, to the signal and the radiative muon decay background went down in some sense. And so the idea is, if you lower your beam intensity, you can lower the photon cut, and that gets you additional signal acceptance and also lowers this background. And so we make a bit of an estimate here what type of reach you would get. So this is the existing twist bound. So these one dwarf and red giant bounds are model dependent. It's because we also turned on the electron coupling. So you're really comparing with twist here, and this is what you'd get for 1 month and 1 year of running in this type of configuration. Where the bands are parameterizing our ignorance because we can't accurately estimate what the trigger rate would be without having a full access to the simulation. So this is entirely theory ignorance, and MEG would not be subject to this type of uncertainties because they know what they're doing and we don't. So that's really the only difference here. And so if you know anyone who might be interested in this, so there are some studies going on at MEC, and so they have shown that there are most optimistic one was slightly too pessimistic, so they can do slightly better than our most optimistic estimate, and they can beat the twist bound, but like about a week of data taking, something along those lines. And so the group of Luca Galli is looking for a postdoc. So if anyone knows someone who might be interested in this, the application deadline is very soon. So. Okay, so we can try to do the same thing at mu3e, and so this in some sense is much less complicated because mu3e is set up to see 3 tracks, which is exactly what this is. And so you can do this analysis offline, so you don't need to like start playing with triggers or like doing different dedicated runs or anything like that. And so what you're looking for is you're looking for the missing mass measurement from reconstructing those 3 tracks. And the background will fall very fast because you're basically squeezing yourself into the regime of phase space where the 2 neutrinos are collinear with each other. And so you're looking for sort of a hump over here, basically. And so if you put this on the same plot, you get this type of line. So this is the MEG curve I just showed you for about 1 month of running. So this thing at phase 1, you would outperform this if you run for roughly 1 month. The 2 black lines over here are the single electron channel at mu3e, and so this is assuming that you calibrate on the Michel spectrum, and this is assuming that you have an independent calibration. So these are the lines that Ann-Kathrin showed in her talk. Again, they're not including systematics, so if it turns out that the systematics can be brought under control, then this is definitely what you want to be doing. But should that not be the case, turns out to be challenging, this is a potential backup plan that you might have. And this higher mass regime, there is no issue with this single electron search, and so you always want to do just 1 electron. There's no point paying a penalty in statistics. You can do the same thing for different chiralities, and the limits slightly shift because there's a slight forward-backward asymmetry that you can exploit because the muons are 85% polarized. But that's kind of, that's just like a neat gimmick, especially if you were to see something, you can try to figure out what current this thing coupled to. Good. Then for the second half, I'm going to talk a little about the flavor conserving case. And so this is also sort of following up on work by Bertrand and Ann-Kathrin. And so the idea here is that instead of radiating off a standard model photon, maybe you're ramming off some dark sector state from either the electron or from the muon over here. And you're looking just for a bump hunt, basically, in the +E- spectrum. And so there are a couple ways of doing this. There's some combinatorial confusion because you don't a priori know which positron pair you should, of the 2 positrons you should combine with the electron. And so there's a couple different prescriptions, but what we just did is like for a given hypothesis mass, you pick the invariant mass combination that's closest to the hypothesis that you're interested in. And so that's this black line over here that you're seeing, this solid line. And so what this does, it slightly sculpts the background, of course, but you can see in the region within the sort of mass resolution that you're looking for a peak, it's essentially identical to just adding them. So we think this is probably safe to do. And it gives us some additional advantages to identify which is the most likely positron that comes from the resonance. Specifically, you can look at the background diagrams. And so there are 4 diagrams if you take some invariant mass combinations like this. So you can either radiate off the muon or off the electron, and then you can cross the legs of the 2 positrons with each other. And so this combination over here, the virtuality and the photon, it will go like the inverse of the invariant mass of this pair. While this one over here, if you pick up the wrong one, so to speak, you get this collinear singularity, which is nothing fancy. That's just something that shows up in QED all the time. But that means that you expect your background to be peaked in this variable while the signal does not have that type of feature. So it's and that's what you're seeing over here. So regardless on what invariant mass I chose to look for, the background is always peaked in the angle between these two, this particular positron and the electron. While the signal, this is some example signal model, but they always tend to be flat or slightly rising like this one over here. And so that's helpful. There are a couple other variables which you can also extract from like just looking at the amplitudes of the signal in the background and figure out that these are beneficial. So this is the type of benchmark that I'm looking at here, some scalar particle coupling either to muons or electrons. If you couple to electrons and you radiate off X from the electron line, it looks very similar to the background if I look at the energy of the secondary positron, so to speak. But it turns out this energy distribution looks very different if you're in the scenario where most of the events come from radiating off the muon line. And so that's an extra handle you have. And then finally, there's the angle between the two positrons also has some features in the background that are not present in the signal. And so we put all these things together, you write yourself a likelihood. In the end, what we need to do, because our Monte Carlo statistics for the background, you generate a couple million events, but at some point, you're kind of running out of juice. So just to be conservative, we only been in two variables, in either, we always use this angle because it's the best, and then either one or the other. And then for this sort of set of benchmarks, we're now also allow for the parity odd coupling. You can sort of see the type of improvement in reach that you can get by leveraging these angles over just doing a standard vanilla bump hunt.
It's an improvement in the coupling?
In the rate. The coupling is the square root of this. Yes.
Is it a Monte Carlo limitation for the scalar cases that gives you the variations, or is that physical?
No, that's physical in the sense that, oh, sorry. We have a lot of Monte Carlo, but like, some of these distributions change as you go from high to low. And so there's some structure to this, just what it is. But it's not entirely obvious to tease out exactly what it is, but it's basically you see your background starts being peaked like this. If you start cranking up the mass, it moves to the middle, and then in the end, it moves the other way, which are all things that we can understand analytically from looking at the decay amplitudes. So this is understood. It's not just MAGRAPH, but I didn't put it on slides because it's a little cumbersome. Good. So yeah, so a factor of 2 roughly in just in the rate, and so without any, just analysis improvements basically. So you don't need to do any difference. There's no difference in how you run the experiment. So for example, if you look at this for the dark photon, so this is a plot that our version of a plot that Ann-Kathrin showed. So if you don't include the angles, you get this dashed line for phase 1 and then this thin dashed line for phase 2. And so these for these curves, we reproduce very well Ann-Kathrin's result and also Bertrand's results from a few years ago. And so this is sort of showing how much better you do if you also include some angular information. We think that this is probably conservative in the sense that we only used 2 variables because of limitations in Monte Carlo statistics. But in a real experiment, you would just be sidebanding this. You extract the background from the sidebands, and you could use all the kinematic information that you have available. And you might be able to do a little bit better. But we do think that the variables that we used are the strongest ones, or the most powerful ones. The remaining ones are likely correlated in ways that are important. And then the second benchmark is, if you have a scalar particle that couples mostly to muons. So what you see here is the coupling to muons, and I fixed the electron coupling here to be always smaller than the muon coupling, but still large enough so that this particle decays promptly, because we only consider prompt decays in this study. And so you see again here that you have some improvement, and there is some reach over here. The strongest bounds here come from this old beam dump experiment, or from the muon G-2 limits right now. For the pseudoscalar, it turns out everything's quite a bit weaker. At only phase 2 has some sensitivity, and the reason is just that there is an unfortunate suppression in the decay amplitude for muons. So pseudoscalars, that's just physics. So this is something that you can just see because the signal rate is just lower. Okay, so that's everything I have. So the idea is that if needed, which is to be seen, there is a way of bypassing systematic uncertainties in the mu plus E plus axion, or like missing energy channel. by either attaching a photon at MEG or by adding an extra like E plus E minus pair. So the MEG one, the mu3e one appears to perform better and has the advantage that it doesn't require an additional dedicated run. However, MEG is already taking data, and so depending on if and when they want to do a run like this, they might get a result earlier. For the flavor conserving case, there are some additional information and kinematic information that we can exploit to like do better without doing any just on analysis improvements. And so we just also systematically went over a number of models that you could consider. I showed you those two because they work, and then there are two in the background that don't work. So that's it.
Questions?
Sorry, just so I just want to understand this improvement in mu to 3e, because there is an extra factor of alpha there, right?
Yes.
So how do you overcome that so that it actually, sorry, I missed that.
No worries. You mean the spot?
Yeah.
Yeah. So, well, if you compare with the single the electron plus missing energy case, you don't overcome it, right? So these limits or these projected limits over here assume that systematic uncertainties are negligible, right? So if that's true, then you should always do that. However, we don't know yet what those will be, and since you're sitting on the Michel edge, which you're trying to use to calibrate your detector, like there are challenges there that need to be addressed. So should these limits in reality deteriorate, then your choice is to either look for a muons plus missing energy and 3 electrons, or with an extra photon, right? And so naively, you'd be like, well, you should always do the photon because it's cheaper in terms of alpha.
Exactly.
Now, it turns out that even with this dedicated run, right, the acceptance for this signal in MEG2 is still really, really bad. And the reason is mostly because their non-uniform B field kills away electrons that are not that are a little bit away from half the muon mass. And so it's just a matter of signal acceptance in that case.
I see.
Well, mu3e has very nice acceptance for the signal because that's in some sense what they were designed for. And they have very low momentum thresholds of 10 MeV, which is really helpful in this for this type of thing.
Thank you.
Maxime,
But this morning we heard from Professor Kuna that if you have this mu on decaying in orbit, right, to a massless particle plus an electron can take a lot more momentum. And with the potential limits from mu to E or comet, would this would this be competitive? Yeah.
So the mu3e one, the mu to E one is this mu EX. This is by Jure, right? But it suffers from a similar issue because you're at the edge where you're trying to calibrate your detector.
Yeah.
The comet one is stronger if you take it at face value, and it would lay somewhere roughly comparative with mu to E. However, as I understood it, like there were no backgrounds included in that search. And also like we had some questions about their systematic as well. So we ended up deciding to not put it here, but arguably maybe we should have.
Probably should fight it out.
Yeah.
I also want to add that the mu3e line is phase 1, right? So
Yes.
phase 2, you might get a factor of 10.
Yes, if the systematics again are under control.
Yeah.
Yeah, so this is phase 1 on mu3e. Maybe we should add that in the label.
Well, you would bound mu to we go out to 10 to 0.
Right.
Assuming that we have some systematics.
Yes.
But we are sort of working towards this.
Okay, that's good to hear. Yeah.
Yeah, I don't see how Comet and mu to E would be much different, but we're working on that also. And Jure is going to show some things about that.
Yeah.
Sure. Yes.
There is also a question on Zoom.
Yeah. And actually, if you look at all the settings, we have that for each of the settings.
Yeah, thank you. Yes.
Hyperclear, right?
I was not sure that I could speak, so I was just waiting. No, just Yeah, just to add a couple of comments concerning the exotic search with MEGII, I cannot mention all of these things due to the constraints in time, but let's say, let me just to go in order. So concerning the first comment about the muE gamma search, as you know, we already, let's say, look at this using the data sample of MEG1. And thanks to, let's say, that the searches, actually, we have been able to actually, let's say, set also there the most stringent upper limit on this potential, let's say, new particle at a level of 10 to minus 11. But let's say with the constraint in energy in the region only of 2045 MeV, because this comes from the fact that we are going to look at this data sample as collected when we are searching for the mu gamma. Okay, and of course we will repeat this search with the new calorimeter, and in principle this should be much better because we have a better capability of rejecting the pileup. So this was probably one of the first things that has been mentioned when Simon was talking. And then concerning the Alps search, we already started to look at some configuration also in terms of beam. And we just at the beginning of the year we did specifically I did some tuning at very low beam intensity on this 2 times 10 to 6 that has been mentioned by Simon, to try to exploit this let's say half searches where we have the muons in A and then gamma. Of course, let's say in the past we put also some effort with some students to look at the muEA, and this specific case we are really strongly limited by the systematic. Nonetheless, when we started to look at that specific channel, we asked ourselves for somehow the first time after several years if the MEGII spectrum was good enough. Because if the MEGII spectrum that you expect to know, it's not good enough, so then you can easily confuse what you should know, let's say, with the new physics. And this actually turned out in a common effort with the theoretical group at PSI, in particular, let's say, with a group of Adrian Signer and the student of us actually did simultaneously theoretical calculation with Adrian about the next leading order for the MEGII spectrum, and then that we put in our simulation, and then we studied also the muEA sensitivity, and there clearly appeared that as long as we are not able to control the systematics, you could not be able to push too much in that direction. And this actually also, let's say, somehow forced us currently now, let's say, to stay focused more on the muEA gamma instead of the channel without the gamma. And let me also to add that, as you know, we are also using the apparatus for completely other different physics. So for example, in the slides that I uploaded, or somehow that have been uploaded by you guys, you can see also in the backup the effort for searching for the X17. So just to complete that, we are trying to also look at other channels. This is all.
Okay, let's thank Simon for the talk and for helping us to put in the workshop. No, we still have 1 more.
No? Yeah. Good.
Okay, our next speaker, also the last speaker for the day is Jure. He will tell us about the MuonBridge. Please go on.
All right, thank you. So I'll have to disappoint Bob immediately. I will say nothing about light new physics, or almost nothing. So what I'll talk about is effective field theory predictions for mu-to-E conversion, and this is done with this group of people. So Wick Hexton, Ken McIlvaine, Tony Menzo, who's my student visiting Berkeley, and Evan Ruhr. All the others are based at Berkeley. Coming out soon. So, so what's the goal? The goal is so I assume heavy new physics. So the scale of new physics will be very large, much above the muon scale. Then I'll walk you through how we use the EFTs, and then at the end there's light at the end of the tunnel, which is this open source code that you can use to get the predictions. So what will I cover? So first I'll go over the scales in the problem. There's a tower of these EFTs. We'll focus on the physics below 2 GeV. I'll have 2 new physics examples of how this matches on, and then I'll have 1 slide about the code. So let's talk about the kinematics. So we have muon. It's captured on, it sits in 1s orbital. And then, so something like this. And then it converts to an electron. This guy flies out. The energy release is 100 MeV or so. So that means that the electron is ultra-relativistic, while a very small amount of kinetic energy goes toward the nucleus, which mostly just takes off the momentum exchange. So we look at the aluminum. The binding energy is a small correction. It's roughly the mass of the electron. So you could basically neglect it in here. So and this will be true for almost any nucleus. This Q will be about 100 MeV, changing by about 5%. So what's this tower of EFT? So if you start in the high energies, so that will be the full UV theory. You will integrate out the mediators. You'll end up in the standard model EFT. Then you run down to lower scales. You integrate out the heavy, so Z, W, Higgs in the top. You end up in a weak effective theory, so it doesn't have these degrees of freedom. And then you run down at each mass threshold. You integrate out degrees of freedom, so B quark, charm quark. Finally, you hit this 2 GeV, and that's where we'll focus on. So we'll focus on the physics here. So what do you do here? So we'll have a weak effective theory that lives at 2 GeV. So it will have gluons, up, down, strange quarks. Then you'll do a non-perturbative matching onto the non-relativistic theory with nucleons. And this will therefore, you'll put them inside the nuclei, and this will give you response functions. On the left, it's the codes that handle different parts of the calculation, or where the calculation is being coded in. So these are public codes out there for the SMEFT running. This is us. No? So the MuonBridge will have 3 components that will handle different parts of this calculation. So several comments here. So this tower, if EFTs, maybe this is for people that have worked on direct detection, this problem is very similar to having a WIMP scattering on the nuclei. There are differences. Of course, I have a non-relativistic dark matter goes into a non-relativistic dark matter. Here, you have a muon that goes into an ultra-relativistic electron. So the change will be that instead of having something that needs to be Galilean invariant, so this Q, the momentum exchange over Mn, now gets replaced by some ultra-relativistic unit vector. The muons, so the initial state is kind of reminiscent of a non-relativistic dark matter. So it is non-relativistic. If you go to heavier nuclei, this will become less and less of a good approximation. However, of course, it's bound instead of a free dark matter hitting a nucleus. So you need to take this into account. There will be also V mu suppressed terms. This will be encoded as lower components of this Dirac wave function. This was all done by Wick and company. The nucleons are bound inside the nucleus. That's the same as for dark matter. Now still we have regular nuclei. These are non-relativistic with kind of 0.2 velocity. The last change is that this outgoing electron has a charge. So it feels the fact that the nucleus also has a charge. There's a trick as to how you handle this. Instead of having an outgoing wave, since the scales here are the muonic atom is still much bigger than the nucleus, that's the approximation. So this muonic wave function is slowly changing inside the nucleus. That's the ratio of scales that you can expand this in. So if you are interested in the event that is happening on the nuclear scales, all you see is a changed outgoing plane wave, which has a different momentum. Instead of Q, it's a Q effective, and this change is about 5% or so. All right, so this may be hard to read, but for aluminum, instead of having 105, it's 110 MeV Q effective that you need to stick in the nuclear part. All right. So we're at this 2 GeV, and we'll talk about the physics that happens below 2 GeV. So we'll start with weak effective theory. So degrees of freedoms are quarks and gluons. So this is what's done in this paper. And then the rest, I will just repeat what Wick company did in the last 2 years. So they go through a covariant EFT with relativistic nucleons. This is not necessary, just for their convenience. So basically, you jump from weak effective theory to a non-relativistic theory. You can think of this as sitting inside the chiral EFT for the nucleus. The degrees of freedom are nucleons, and the chiral countings then guarantees you that if you work to leading order, you only need to care about the single nucleon currents. So that's what's being done. All right, so the weak effective theory. We're seated to GeV, and we work up to dimension 7. So unfortunately, since I talk about EFTs, I have to show the operators. So there will be many operators, but I will try to motivate what's interesting. So the dimension 5, so expand this. There's a grouping in terms of dimensionality. The higher the dimension, the more suppressed these are with this heavy new scared. So if it is dimension 5, it's 1 over lambda. Dimension 6 is 1 over lambda squared, and so on. The heads means that these Wilson coefficients have dimensions. If they don't have heads, they're dimensionless. At dimension 5, there are 2 operators, the magnetic and the dipole one. So if this would be, if this were not flavor violating, this would be CP even, this would be CP odd. At dimension 6, there are 10 operators. They are of the form of vector current, so either vector or axial. So that's these 4 combinations. So either vector axial on the leptons or vector axial on the quark side. Then it's the same story with the scalar versus pseudoscalar. So either scalar or pseudoscalar on the lepton, and the same for the quark. So that gives me another 4. And then there are 2 tensor operators. So that's the 10. Now you see that this is something that if you were to work in SMEF, you would not choose this basis because it's not left-right, but it's rather vector versus axial. So the reason why we do this is, of course, that it has nice non-relativistic limits. To convert between the 2 bases is trivial. Now it's just linear combinations that you need to do. The same for the quarks, because it's much easier to write down hadronic matrix elements. And the other thing that I should really point out is, here, the tensor operators really appear at dimension 6. No? All right. Okay. Then if at dimension 7, there's 16 operators. There's 8 which couple leptonic currents to the gauge bosons, so either gluons or photons. So if this was, let's say, just a muon, this would be like a muon polarizability operator. And it's just different CP properties. So either you change the CP on the lepton or the gauge currents. And then there are 8 operators that come with derivatives. And you can, with equation of motions, you can move these derivatives to all sit on the leptonic currents. So again, the reason why I want to do this is then it's very easy to write matrix elements for the core currents. All right, so that's the basis. It's a full basis at dimension 7 with some convenient choices because you work at low energies. You're not really interested in the SMEFT part. So there will be some conversion there. All right. Now we go and we need to match now to this non-relativistic theory with nucleons. Here there's a non-relativistic expansion that happens. I already mentioned a little bit this. There are basically 3 scares there. One is the fact that the muonic atom is much bigger than the size of the nucleus. That's this first parameter, which is so this is this V mu tells me that this is a small velocity. It's much smaller than the velocity of the nucleons inside nucleus. And the velocity of the outgoing target, the whole nucleus, is even smaller, right? So that's the hierarchy. So you go, this you can completely neglect. This will be at a few percent level. This is at the 20% level. And this Q over B is, I don't know, how B is the nuclear size. So this will be, I don't know, 20 to 50%. So you want to keep this to all orders. You can expand in the nuclear and the muon velocity, and you can neglect the fact that there is a momentum that goes into the nucleus. So that's the expansion that is being done. So the leading effects are then captured by having non-relativistic operator, where you would, for instance, you could go to the 0th order in both of these. But what Wick and company call leading order is they go to linear order and Vn, mainly because previously people have worked to leading order in V mu, which is a smaller thing. And that's the basis. All right, so that's the non-relativistic basis. So if people that have worked in direct detection, which I see at least one face that did this in the audience, this looks very similar to the basis that was used for direct detection, except there are 2 new operators. So instead of 14, there are 16 operators. And some of them have primes here. So these are rearranged. They look differently. And instead of Q vector, you have a Q head. So it's deceptively similar, same, but different. No? Then if you, doing the same thing. All right, so if you also include the V mu suppressed terms, then you have an extra 10 operators. And what I should point out is that this thing includes the operators that are not suppressed by any velocity suppression, like O1 and O4. There's, for instance, this guy also is not suppressed, O10, O8, etc., etc. Oh, sorry, not the O4, O10, etc. There's the O11, and then there are also velocity suppressed. It's all mixed in this notation, but still there's a hierarchy there between these operators. So how do you match onto the non-relativistic theory? So all you need to do is do a non-perturbative matching from the weak effective theory to this theory where your muons interact with the nucleons, convert to an electron, and what you need to do is just write down the hadronic matrix elements for these currents. So and this then translates into the Wilson coefficients in the non-relativistic theory. So in other words, you take wet, this fixes this, the particle physics sits in these Wilson coefficients. The hadronic physics hits in the form factors, and you get a coefficient in the non-relativistic effective theory. So so this was a lot of formulas. I had one more slides, and then I'll try to summarize what's important. All right. So I need a little bit more of the language. So what do you do with this? Now you take the matrix element squared, you put it into the nuclei, you will end up with what's called the response functions. These response functions are the W's here. So these W's, and you see that this was already ordered in terms of, that's the rate for the conversion, some prefactors, and then the kinematical factors, which contain these Wilson coefficients. If you see Q effective squared, that's the Vn squared suppressed piece. This is the interference term. And there are 6 different response functions plus the 2 interference response functions. All right. All right. So that was a lot of details. So let me zoom out. So there were these response functions that correspond to the property of nuclei. The first one, the Wm, is just the total charge or the coherent part of the mu2e conversion. So in the Q to infinity limit, so in the long wavelength limit, all this does is count the number of neutrons and protons inside the nucleus. You square this and you get an A squared enhancement. There were 2 response functions, sigma double prime and sigma prime, that said there. So this measured the longitudinal and the transferred parts of the spin operators. Right? So that's kind of different what was done before, but very familiar from dark matter. There's a preferred direction, so there will be a longitudinal and the transverse pieces that will enter. So there are 2 response functions associated with the spin, not 1. In the long wave limit, they are the same, or up to some factor, normalization factor. They're the same response function. Then the remaining 3 have to do with the distribution of velocities or angular momenta inside the nucleons. So basically what they tell you is the composite structure of the nucleon. So these are the ones which really probe the fact that the nucleus is composite. They don't have a non-zero no velocity limit. And interestingly, this F double prime has coherence over half field shares, which you can also see if you expand in the non-relativistic expansion. So the rough scalings is you have the contributions from the Wm, this coherent piece goes as A squared. Then there are 3 which are roughly of the same size, the spin and the coherently enhanced piece, but velocity suppressed, is of the same size numerically, and then the rest. And then there are 2, the interference terms that I didn't write, plus the order V mu suppressed pieces, which I also didn't write. Okay, so further comments. So what's going on? So if you completely got lost, maybe now you want to come back, because that's maybe quite important. Because the main difference between dark matter and mu2e conversion is that this momentum exchange is fixed. So there's just one muon goes into it gives the energy to the final state. Nucleus is very heavy, and the fact that you have a charged an electron going out in the charge potential of the nucleus only has an effect at the 5% level. So this Q effective is basically constant, which means that all these coefficients that sit in the non-relativistic effective theory are basically constants. No matter what target you choose, there will be basically the same numbers up to 5%. All right, that has a very important consequence, Because if you work at the leading order, so the Vn to 0, V mu to 0, there are only 3 combinations that you will ever probe. No? So there are 3 numbers that you will measure. Doesn't matter how many nuclei you pick, you will only measure 3 numbers. That's at the leading order. So it corresponds to vector, scalar, axial, and pseudoscalar currents, basically. Now, if your calculations are precise enough, and you have stamina to do more nuclei, so conversions on more nuclei, you will be able to measure 5 combinations. Here, I only do isoscalar counting, so there are then 3 times more numbers. So here would be 9. In reality, it's only nucleon coupling to nucleon and protons. There's only a finite number of numbers that you will measure. I can talk in details what exactly you can measure. So the end point is it's very important to measure both mu to E conversion on many nuclei. But you see that mu to E gamma will be quite important to break degeneracy. And then if you're interested in the leptonic currents, of course, mu to 3E. Okay, all right. So now a few words about this code. It has 3 components. So what this has is a muon converter, mu to E, non-relativistic ET, and elastic. So this muon converter does the matching from weak effective theory to non-relativistic theory. And there's an interface with the physics above the 2GeV. The mu to E NRET calculates this conversion rate normalized to the capture. The particle physics comes from muon converter. So this you put in the Wilson coefficients and it spits out the rate, and it reads in the nuclear physics from the elastic repository. All right, comes both in Python and mathematical versions. All right, so let me do 2 examples just to highlight. So I'll do 2 examples. One is the leptoquarks and a light ARP for 2 different reasons. So the leptoquarks, I picked one. It's not really important. It's a triplet, doublet. It's 7/6 of the hypercharge. Has 2 types of couplings. So visually, you have muon goes to a quark goes to an electron with a heavy guy that you integrate out. All right. This is complicated enough that you generate all 10 dimension 6 operators. All right. So you end up with all these guys. And in particular, you have the tensor currents, where there are these surprises that at subleading order, there's a coherently enhanced piece. So you would miss by order 1 if you didn't include these Vn suppressed pieces. No? So it's important to include these seemingly higher order terms. The light ARP is a different example for a different reason. So I had this assumption of heavy new physics, which is the usual thing when I can talk about the EFTs. But in this case, it's very easy to include also light mediators, because all they do is they will talk between the leptonic current and something that is like gluons or quarks. It's impossible to have light new physics that couples with order 1 couplings to gluons or quarks. So this will necessarily be a 3-level exchange, or it will not correct the QCD at any significant order. So all you need to do is now promote these Wilson coefficients to be Q² dependent, and all the rest goes through. So you can just use the code. All the calculations go through unchanged because you don't change QCD. Even better, this Q² is really just a constant in this. It's just one number. So these really are just coefficients. So the mu to E prediction doesn't care that there's really light physics happening. So there's nothing in the calculation that will change. All right. That was the last physics comment. So the rest is conclusions. So what did I talk about? I covered an EFT approach. This is the mu-to-E conversion is perfect for this. There's a separation of scale. Problem factorizes as soon as you use this trick of Q effective. And then I presented results that include up to dimension 7 operators in weak effective theory and the subleading effects in the non-relativistic effective theory. And the most important thing, now there's a black box that you can run. It's called MuonBridge, and it will be available soon. Thank you.
Thanks, Jure. Just a quick question. In this formalism, can you use some kind of orthogonal data sets to constrain some of these operators, especially the nuclear physics associated with it? Or so, for instance, I'm thinking, could radiative muon capture, for instance, tell you anything about this?
Muon capture, I'm not sure. You need to. I'm not sure that it will help. It will help in terms. You mean you're interested in the new physics part, right? So if you change the Q squared, yes. If you change the Q squared, then you presumably will be able to distinguish the Q dependence there. No, the Q dependence will be different. I should maybe go back to this basis, and you'll see where it enters. All right. So there are two types of things. No, so you have. So the form doesn't change. Now you still have a Q hat sitting here. However, the Q squared that will flow into the response function will be a different one. So the response function itself will look different. No? So So in here, no. So you will change the value of these guys relatively. So you will be able to, for instance, without doing different nuclei, maybe, no. You will be able maybe to pick out what is the difference between this and that. No, does this make sense?
Sure.
So
yes.
Apart from that, that's about it. No, the rest of the counting still works. No, I think. Right. I don't have a good enough feel. I would have to look at the formulas to tell you if,
the other question I had,
orders it breaks anything.
Kind of related is. So to learn about these response functions, I presumably you have to have data from somewhere else, right?
Oh,
so
that's okay. So this is just nuclear physics, no? So any measurement that probes the nuclear physics of this nuclei, let's say aluminum, that's where you will fix this response function. So all the scattering data. So what goes into this now is it's a whole industry, you know. So you need to do a global fit to the nuclear potential. So the interactions between N, so N. So 3 nuclear currents, 2 nuclear currents, and does this make sense? So you fit for the potential. Right now, most people like to do chiral perturbation theory inspired.
Well, what's the data that comes in?
Nuclear scattering, the pi scattering, nucleon scattering, the spectra, the magnetic moments. So all the observables that you can think of in the nuclear physics. No? You do a global fit. They hand you a potential. You take this potential and then you do your favorite thing. So what these guys do is
I ask because the 100 MeV kind of energy exchange, like how well can you probe that with low energy nuclear physics? Right? In principle, you need
that's the domain of nuclear physics. They were born to do this stuff. Yeah.
There is a lot of older literature on the ordinary muon capture, right? Nuclei. Okay. And unlike the BSM, where like I guess the main difficulty is that you have very many animals and you don't know how many cages you put them in. There you need to calculate things to a higher precision. And in the past, there was like a lot of efforts done, right? Triumph in particular by Harold Fearing and others. And in particular, this what you're showing, the axion propagator, right? In nuclear physics, of course, it'll be a pion propagator, and there was a lot of this. Have you looked at? I mean, you're referring to the dark matter efforts, but
yes,
this is all theoretical. The other things relate to data.
yeah, exactly. So I anticipated the different questions. Let me answer the question that I anticipated and the one that you're asking. So there's a lot of work that was done on both fronts, also the BSM and the standard model one. The difference, the big difference is that there you always have a coherent piece which dominates. So there's less emphasis on, you know, getting the rest of it to, you know, some things will just be well below the precision that you care. However, a lot of I mean, all the tricks here were developed for other reasons. So this is, so Wick and company just put things together. So this trick of Q effective came from the electron scattering. The response function formalism was done for the dark matter, but was really done before for the beta decay already. No? So it's all old stuff. So that's the standard model part. Now the question that I anticipated and I put in the backup slide. So that's the literature. Evan collected this in their paper. So there's a lot of literature that was done on the muon conversion. And this is what the approximations made were done. And you see that none of this expanded in Vn, which is bigger than V mu. V mu is here. No? So what they did with the psi mu and the psi electron here. And then there were spin corrections. So if you pick, for instance, I don't want to be, but let's say I pick, I don't know, let's say these guys. No? So they already have the leading effects. However, there's no correction for this Q to Q effective. So I don't know how much you care. No, it's 5%. But if you care about the tensor operators, this is not there. No, so the piece that is of the same order here, for instance, is this phi double prime that would be missing. There's I don't know. Yeah, but there's of course a lot of literature.
Well, when you do normalization, you normalize just on the number measured, or you normalize on some theory?
Yeah, that is a good question, which we didn't settle on yet. So the code is not public for us. No, I mean, what they did is different than what maybe will be in this version 2. So,
if you the charged rate will have a different response function. Are you going to normalize on exclusive rates?
You mean on the standard model?
Yeah, that's right. Or on the inclusive.
So right now it's on the inclusive rate. Okay. Yeah.
So very naive question from experimentalist. So presumably this framework is can be used to select what kind of nucleus to get all this information.
Yes.
To do this, once this response function is given, and then we can choose what kind of a nucleus should be used to determine all these parameters or something. Is that
Yeah, that's correct. Yeah. So right now, in this, so here, no. So in this repository, where was this? Visually. So these guys, no. So there's this elastic part of the repository. It's just a list of files for the different nuclei. And of course, it doesn't matter what you use this for. Half of them are because there are dark matter experiments. So there's a lot of xenon files there, germanium, silicon, aluminum. I mean, it's a whole list. I think carbon is there. Some lighter ones. I don't know. Carbon is there. I don't know. It's a long list that is done already, but you could just add more. Yeah.
But
Ann-Kathrin is not there, I think. I'm pretty sure. Yeah.
But in the end, I think we have to choose which target is sort of give us orthogonal information.
Yes.
And so on and so forth.
Yeah. So I think what you're asking is maybe so right now what is being done is this is a shell model calculation. You could just do something else to calculate these response functions, and you could just add your own files to the repository. But yeah, it has to be, somebody needs to calculate the response function in order to answer what you are asking. Yeah.
And also, I'm interested in the dimension 7 operator.
Yes.
So once we know that the response function, then we can just pick up this what kind of nucleus is better to get dimension 7.
Yeah. So for dimension 7, there's nothing new in the terms of the response functions. The problem there, maybe I should go back now. So sorry. I had this list. Maybe it's good to look at this. So for instance, the matrix element for this is known, nuclear matrix element also for this guy. This is just an estimate, no? Because you not entirely, that's just an estimate. So somebody would need to calculate this matrix element of 2 photons attaching to nucleons. Right now, maybe it's Itano or some. You can do models, no? You can just do.
Large nucleus is going to be coherently enhanced, right?
It's absolutely coherently enhanced, but there's always a non-perturbative piece where, so you could just do an estimate where you do a 2-photon loop. There's gonna be a piece where this propagator just overlaps, no? That's the matrix element that you don't know. So this is not fully known, but you can do a model and it will be fine until somebody calculates the matrix.
Over nucleons is known, right?
Yes, but that's not the full piece.
Yeah, okay.
Yeah, that's why. So it's good enough to ask a question whether you want to work on a particular target, but if you really want to interpret, once you see the discovery, I mean, you'll just ask a lattice friend and they will calculate this matrix. Yeah. It's also a piece that there's the 2 body currents potentially important here for the 2 photons.
Also, I saw that you said that a muon wave function is larger than nuclear, but then that's not the case.
For aluminum, yeah.
For aluminum, yes, but most of the case, it's even smaller or comparable.
Yes.
So particularly heavy.
Yes, absolutely. Yes. Then, yeah, that's where you would maybe want to start questioning this Q effective trick, because your wave function will start. I mean, they argue that it's still fine, but you can really start questioning, no? Yeah. And you could. I think you could do a really even more EFT-based approach there potentially, but it was not done. So, yeah.
Okay, let's thank the speaker. Okay.
dinner on the agenda, and the locals will know where that will be. It's basically McNamara building. It's up within your phone. If you're alone, then we'll show you where to go. It's as you enter the building, I think it's to the left, and so it will be. If it's in the same style of dinner as before, I remember it, then there would be drinks before dinner and then kind of a buffet style dinner. Most likely, that's what they do.
Should we wait until
We're
5:30?
gonna go over there. Over there in an hour, follow you. I think we can show up a little earlier, but. I need to do that.
Nicholas says it is grown $5.
Yeah. We wanna like drop their stuff off.
Maybe basically, maybe 10.
Yeah, I mean, either way.
That's gonna answer that.
Yeah.
That's not Susie. That's not Susie.
That's what I was trying. Yeah, it's like it's competing.
These days, I'm happy to pick you.
They're both so close that I'm not even sure what this is.
It's the same as
The thing that they don't know is how numerically different this response functions really are. Yes, because by the time, like, even after your electric, you don't need a and that
Square.
they have the same. They're not set up for it. I mean, you can do it. But I don't.